Hi everyone, good morning, very good morning to everyone. So how are you all? Hope you are all doing great. So welcome to marathon program of algorithms. Okay, in this program we are going to discuss briefly most important concepts related to the from the subject algorithms, okay, related to the GATE examination. So I will try as most as possible not only solving the question, we also going to briefly revise the concept, key points. So we going to be revise key points as well as we going to be solve the problems. Okay, so session maybe 4 hours or 5 hours depends on the kind of means the response from your side and as well as hello. Hope you all ready. So we are going to discuss almost all important topics related to the algorithm subject, and not only solving the problem, we are also going to discuss key points, okay, like a complete revision of the subject. Okay, so I hope you all ready. Good morning to everyone. Hope you all ready. Good morning to everyone. Satyam, Sampati, Akash, Deepshika, Avinash, good morning to everyone. So yeah, let's move to the first topic. Okay, so asymptotic notations, almost last many years. So one multiple selection question or one multiple choice question used to ask from this topic. Okay, so let's see the key points of the asymptotic notations. Okay, so to prove f of n, to prove g of n asymptotically bigger than, to prove g of n asymptotically bigger than f of n. Okay, so this one, g of n asymptotically bigger than f of n. So this is the mathematical expression. Okay, to prove g of n asymptotically bigger than f of n. So mathematically we have to prove that limit n tends to infinite f of n by g of n equal to, okay, equal to infinite. If limit n tends to infinite f of n by g of n is infinite, it means that f of n asymptotically bigger. Limit n tends to infinite f of n by g of n is infinite, f of n asymptotically bigger, this numerator function is bigger. Okay, limit n tends to infinite f of n by g of n is 0, then this denominator function asymptotically bigger. Limit n tends to infinite f of n by g of n is 0, this denominator function asymptotically bigger. Okay, now limit n tends to infinite f of n by g of n equal to constant, both are asymptotically equal. Okay, so means this is may required for theoretical question also. So asymptotic comparison between two functions, something like this. Okay, So we apply limit n tends to infinite. So f of n by g of n, okay, f of n by g of n. So three choices for the answer, okay. Limit n tends to infinite f of n by g of n if it is infinite, okay. F of n asymptotically bigger than g of n, okay. So if it is 0, f of n asymptotically smaller than g of n. If it is constant, f of n asymptotically equal to g of n, right. So this is one important point we need to revise from the asymptotic notations. And so f of n big O of g of n if and only if g of n asymptotically bigger than or equal to f of n, okay. So f of n big O of g of n if and only if g of n, f of n should be asymptotically smaller than or equal to g of n, okay. These all definitions so is known to you, okay. So now see, these are the key points before going to the problems, okay. So we already just discussed this one, okay. So now f of n, these are the basic things from the notations. F of n big O of g of n means f of n asymptotically smaller than or equal to g of n. So f of n omega of g of n, f of n omega of g of n, it means f of n asymptotically greater than or equal to g of n, okay. So f of n theta of g of n, it means f of n asymptotically equal to g of n, okay. So f of n little o of g of n, it means f of n asymptotically only smaller than g of n. So here big O is allowed to represent asymptotically less than or equal, little o is allowed to represent asymptotically smaller than, okay. F of n little omega of g of n, it means f of n asymptotically greater than g of n, okay. So f of n big O of g of n, we can also say g of n is omega of f of n, okay. So f of n little o of g of n, we also can say that g of n little omega of f of n, okay. So these are the things related to, okay, implied, okay. So f of n little o of g of n, little o of g of n, then we can also say big O of g of n. Reverse of the statement is not true. F of n little omega of g of n, then we can say f of n is big omega of g of n, okay. So we are going to solve the problems, okay. Just go through the these meaning of each symbol in the asymptotic representation, right. Good morning everyone. Good morning Sangeeta, Satish, Sudhir Babu. Right. So hope you have basic idea. Let me know any of this having any issue. Right. Now try this question. So which of the following statement is or true? Which of the following statement is or true? Okay, so f of n big O of g of n implied g of n big O of f of n. F of n plus g of n is theta of minimum of f comma g. Okay, f of n is theta of f of n by 2. Okay, f of n plus little o of f of n is theta of f of n. Nikhil Pandey, Shivani Sharma saying C. Right. Okay. So f of n is big O of g of n. So just before we discussed f of n big O of g of n. It means that f of n asymptotically smaller than equal to g. F of n big O of g of n. Okay, so it is logically means that, okay, f of n must be notation of other side, notation of other function, minimum of f of n plus g of f of n comma g of n. Okay, so whenever this kind of format question is given, just apply asymptotic comparison between these two functions. Asymptotic comparison between these two functions. If asymptotic comparison is, okay, less than equal, then we can use big O. Greater than equal, we can use omega. Equal means we can use big O, omega, theta. Okay, like that, based on asymptotic comparison, we can see this given symbol correct or not. Okay, f of n plus g of n. Okay, so comparing with the minimum of them. So the possibility is, so this can become asymptotically greater or equal to this minimum of among them. If both are f of n, g of n both are asymptotically equal, then minimum is also asymptotically equal to f plus g. Okay, f and g are not asymptotically equal, then minimum is become asymptotically smaller than f plus g. So here only applicable notation is omega. Okay, we can say omega of minimum of them. So but he is saying that theta. Okay, so this is also false statement. Okay, then third one, f of n is theta of f of n by 2. F of n theta of f of n by 2. Okay, so see, if f of n polynomial function, something like n square, so definitely f of n, okay, so f of n by 2 are asymptotically equal. So n square, okay, can be written as n by 2 big O, so theta of n by 2 whole square. It is correct only for polynomial functions. Okay, because of polynomial function, okay, if n is a if it is a polynomial function, n is in the base side, so n by 2 whole square is asymptotically equal to n square. But in case f of n is exponential function, okay, so 2 power n is f of n by 2 is 2 power n by 2, right? 2 power n and 2 power n by 2 not asymptotically equal. 2 power n and 2 power n by 2 not asymptotically equal. So this is also not correct. Okay, false statement. Okay, so now the fourth statement. So this fourth statement, f of n plus little o of f of n is theta of f of n. So whenever this kind of questions are given, f of n plus little o of f of n, okay, is comparing with the f of n, okay, so theta of f of n. So whenever this kind of question is given, just asymptotic comparison between before equal and after equal function. Before equal, after equal, what is asymptotic comparison? So see, little o of f of n, okay, we can say little o of f of n, okay, so that means right side function is f of n using the little o. So assume that little o of f of n is some function g of n. What can be the possible choice of g of n? G of n can be any function, g of n can be any function which is asymptotically smaller than f of n, okay. So g of n can be any function which is asymptotically smaller than f of n. That means little o of f of n means, little o of f of n means some function which is asymptotically smaller than f of n, okay. So this is the sum function, okay, it can be any function, okay, any function asymptotically smaller than f of n. One function asymptotically smaller than f of n, and f of n, it means this is the leading term, okay, this is the leading term, this is the maximum term, okay. So maximum term, and it is greater than the second function also, maximum term, it is greater than the second function also. If those such a two functions are added, leading term is f of n only, leading term is f of n only, comparing with f of n, so it is asymptotically equal, okay. So it is asymptotically equal. Asymptotically equal means big O of f of n also true, omega of f of n also true, theta of f of n also true, okay. So big O of f of n also true, omega of f of n also true, theta of f of n also true, because asymptotic equal allowed for big O notation, omega notation as well as theta notation. So D is a true statement, right. Is this fine? Is this fine? Pravaz. Right, Nikhil Pandey. Now one more question, okay. Which of the following statement is or true? Similar to this model question. So whatever we discussed here, okay, apply same concept. Whatever we discussed here, apply similar concept. So which of the following statement is or true? Okay. So of course the previous question is also used for two options, okay, this left side function, and two other options is given. Nikhil, Prajwal, Satakshi, Sagar, okay, clear that one. Sambhav, Smith, Uttam, right. So again little o of f of n, little o of f of n, assume that right side function is given, little o of f of n, assume some g of n. So what is the possibility for this g of n? So the g of n, little o of f of n means g of n should be asymptotically bigger. So this g of n is any function, g of n is any function which is asymptotically smaller than f of n. Okay. So similarly, okay, assume that little omega of f of n, little omega of f of n. Okay, let's say some other function g of n is little omega of f of n, means g of n should be greater than f of n. This can be any function, this can be any function which is asymptotically, okay, so f of n should be asymptotically smaller than g of n. Okay, this should be asymptotically, okay, so greater than f of n. This should be any function, this g of n should be any function which is asymptotically greater than f of n, is the little omega of f of n. Little o of f of n means this g of n can be any function which is asymptotically smaller than f of n. Okay, so now option A and option C both uses same LHS. Option A, option C both uses same LHS and comparing with the f of n, okay. So we need to see f of n plus little o of f of n, plus little o of f of n compares with f of n, right. So the little o of f of n means this is any function, okay, any function which is asymptotically smaller than f of n, okay, plus f of n means f of n is leading term, okay, f of n is maximum term out of these two. So comparing with f of n means it is asymptotically equal. Asymptotic equal is the comparison. Okay, if asymptotically equal, so we can allow big O also, omega also, theta also. Okay, so big O of f of n also true, theta of f of n also true. Okay, both these statements are true. Okay, even if we can write omega of f of n also. Okay, now other two options uses, okay, f of n little omega of f of n plus little omega of f of n in the LHS side. Okay, so now f of n plus little omega of f of n comparing with, okay, this summation is comparing with f of n function, right. So f of n little omega of f of n, it means it can be any function which is asymptotically greater than f of n. Okay, this is asymptotically greater than f of n. Okay, this is any function asymptotically greater than f of n, right. Okay, so that means this term is maximum term, this term is leading term or maximum term. Not only it is maximum term, it is greater than f of n also, not even equal. Okay, so it is guaranteed greater than f of n. That means that summation asymptotically greater than f of n. That summation asymptotically greater than f of n. Okay, this total LHS side asymptotically greater than this RHS side. Okay, it means that it can be used little omega also, or it can be used big omega also. Only these two are applicable. So left side function asymptotically greater than right side function means we can say little omega of f of n also true, big omega of f of n also true. Okay, big omega of f of n also true as well as little omega of f of n also true, but not theta of f of n. Okay, but not theta of f of n. So answer to this question A, B, C, right. So many are answered. Okay, so Siddhi, Nikhil, Jay Surya, Divya Bharti, Sagar, Jaydeep, Nishu, right. So hope you cleared that one. Post your comment. Lot more conclusions going to discuss. Okay, so we just made few statements only, before solving first two problems. Okay, so because these are the basic notational meaning of the each asymptotic symbols. Okay, only we use it so far. Now try these two questions. I'm displaying two questions at a time. Okay, next question also I am displaying. So a small difference between first and second. Okay, try these two. Ankit Yadav. I am fine, Ankit. How are you? So, from the Calcutta batch. Right. Yeah. So, again same like a previous technique. This total summation is LHS. This total summation is LHS comparing with the function n square. Okay, that means big O of n square plus, okay, omega of n square plus theta of n square. This total summation comparing with the function n square, options n square, all options uses n square, only notation symbol is changes n square. So here between these two, what is asymptotic comparison? Between these two, what is asymptotic comparison? Okay, so big O of n square means any function which is less than equal to n square, some function which is less than equal to n square asymptotically. So omega of n square means it can be any function which is asymptotically greater than equal to n square. Okay, theta of n square means it is asymptotically equal to n square. Okay, so big O of n square means some function, okay, which is asymptotically less than equal to n square. Omega of n square means, okay, some function which is asymptotically greater than equal to n square. So theta of n square means, okay, some function which is asymptotically equal to n square. Okay, so less than equal to n square plus n square, less than equal to n square plus n square. So compare to these two, compare to first and third, and this theta of n square is greater or equal to this function. Theta of n square is greater or equal to this function. This one is less than equal to n square, this is n square. Means minimum value of the summation is n square. Minimum value of the summation is n square, or it can be more than n square also. Minimum value of the summation is n square, or it can be more than n square also. That means overall summation asymptotically greater than equal to n square. Okay, so overall summation asymptotically greater than equal to n square. Greater than or equal also possible. Okay, so only possibility to use notational symbol here is omega. So the answer to this question is omega of n square. Okay, the same thing here. So multiplication is used. So big O of n square plus multiplied with omega of n square multiplied with theta of n square. Okay, see, this is less than equal to n square asymptotically, and this is greater than equal to n square asymptotically, and it is equal to n square asymptotically. Okay, less than equal to n square means it can be too small also, decrement also. Greater than equal to n square means it can be too big also. Okay, too big also, and it is equal to n square. So the overall, okay, for example, if you compare with the n square, okay, if you compare with the n square, so in case this is the decrement function, it is n square and it is n square. Overall can be, it is asymptotically smaller than n square also, or overall multiplication can be asymptotically greater than n square also, overall multiplication can be asymptotically equal also. Okay, we can't say only asymptotically less than equal or greater than equal or equal. Okay, so for example, if this is 1 by n to the power of 10, big O of n square is also can possible 1 by n to the power of 10. Okay, in case it is only n square, it is n square. In this case, overall multiplication is become asymptotically smaller than n square. Okay, otherwise if all are n square, then it is become asymptotically greater than n square. Okay, smaller also possible, greater also possible. Okay, so we can't say big O of n square, only omega of n square, only theta of n square. None of them is correct answer. Right? Yeah. Akash, Ankit Yadav, Satyam cleared that. Second one, Aman Pandey. No, even if MSQ, we can't say ABC. So if you say big O of n square means it should be always big O of n square, not one particular example big O of n square. Okay, so even for MSQ also it can't be ABC. Okay, it can't be ABC. Okay, still it is none of them only. So whenever we see, here we are saying that omega of n square, right? Omega of n square. So it is going to be true for every case. Okay, you can take any function which is less than equal to n square, or any function which is greater than equal to n square, any function which is equal to n square. Overall summation guaranteed asymptotically either equal to greater or equal to n square. So that means it is even if it is multiple selection, you should not say big O of n square and theta of n square because of it satisfied one particular example. Okay, whenever in the notation, whenever some statement is true, it should be true for all the functions related to that category, right? Now this is one of the PYQ question. Okay, just for revision purpose I written here. It is not a new thing, it is one of the PYQ question. Okay, just for revision purpose I displayed this question. So parallelly I will display one more related to the same. Please solve the first one. Nishushes D, Harsh Krish, Akash Chaudhary Sagar, yeah, second question 25n. Okay, is the second question 25n, cos 25n. Yeah, first question already explained. Okay, so this is one PYQ question. Okay, so you might have already seen this question. Okay, it's a PYQ question. Yeah. Right. Okay. So sine value is range between -1 to +1. Okay, sine value is ranges between -1 to +1. Okay, so this f of n function, so n to the power of 1 plus sine n, n to the power of 1 plus sine n. Okay, the sine n ranges from okay -1 to +1. Okay, so by the time of, it's not like for small n values it's -1, not like that. Even for large n value it is also still toggle between -1 to +1. Okay, even if you take large n value also, sin n can be -1 also, 0 also, +1 also. It is ranges from -1 to +1. Okay, whereas g of n is root n. Okay, g of n is root n. Okay, so by the time of sin n +1, the f of n is bigger. By the time of sin n is 0, also f of n is bigger. By the time of sin n is -1, in that time g of n is bigger. Okay, so not always one function greater than or equal to second function. Okay, not always one function greater than equal to the second function. So if you plot the sample graph, okay, so now assume that this is f of n g of n function, this is f of n g of n function, and these are n values. Okay, these are n values, right? So now this g of n is root n, continuously increases. Okay, g of n is root n, whereas f of n is from n power 0, okay, sin n is -1 means n power 0 to n square. Okay, so it can become n square at least n power 0, 1, n square at least n power 0, something like this. Not always one function bigger than other function. Okay, not always one function bigger than other function. So this kind of scenario is functions not asymptotically comparable. F of n, g of n not asymptotically comparable. Okay, so it is not, means no one is always asymptotically smaller or equal to or greater than other function. Okay, so whenever asymptotically not comparable, neither f of n big O of g of n nor g of n is big O of f of n. Okay, so neither f of n big O of g of n nor g of n is big O of f of n. Okay, now if you see this second question, second question, okay, so cos phi I, phi multiplied with I, cos phi I, where I is, assume that 0 1 2 3 4 integer. where I is 0, 1, 2, 3 up to so on n integers. Okay, this value is minus 1 whole to the power of I, minus 1 whole to the power of I. Okay, here he is used cos 2 phi n, n is integer. Okay, cos, okay, 2 phi n where n is integer. Okay, so in this case this phi multiplication factor always even number, this phi multiplication factor always even number, cos 2 phi n where n is 1 2 3 4 integer. Okay, so where n is 0 1 2 3 like up to so on is integer, even if you take large n value. Okay, so this phi multiplication factor is like even number, that means minus 1 to the power of even number, this cos 2 phi n is plus 1. Okay, cos 2 phi n is always plus 1, that means this first function, the first function is n square, the first function is n square, second function is root n, second function is root n. So f of n asymptotically greater than the g of n, f of n asymptotically greater than the g of n, f of n asymptotically greater than g of n means that so f of n big O of g of n true and g of n, okay, g of n big O of f of n, okay, so is false, right. So n square big O of which option is correct, not this one. Okay, so n square big O of root n is false. Okay, f of n big O of g of n is false. Okay, n square root n big O of n square is true, g of n big O of f of n is true. So that means overall f of n asymptotically greater, f of n asymptotically greater than the g of n. Okay, is the conclusion. F of n asymptotically greater than g of n means g of n big O of f of n true, f of n not big O of g of n. Is it fine? Is this cleared? So first question all are answered because it is POQ, but second question many are given D as well. Okay, the second question, this cos 2 phi n is not like a range from minus 1 to plus 1. Cos 2 phi n where n is integer, it is always plus 1. Okay, so always plus 1. So this first function is n square and second function is root n. So n square asymptotically greater than root n. Right? Is it okay? Clear this one? Goswami, Rudra. Okay. So before solving next question, one more note. Before solving next question, one more note. Okay. So to compare f of n, g of n growth rate. Okay. To compare f of n, g of n growth rate, we may require to apply logarithms. Okay. We may require to apply logarithms. Okay. Log f of n asymptotically bigger than log g of n. Log f of n asymptotically bigger than log g of n. Okay. So this one. So log f of n asymptotically bigger than log g of n. Guaranteed f of n asymptotically bigger than g of n. Guaranteed f of n asymptotically bigger than g of n. Okay. But log f of n asymptotically equal to g of n. Log f of n asymptotically equal to log g of n. Okay. F of n, g of n may or may not asymptotically equal. See, f of n asymptotically, log f of n asymptotically greater than log g of n or log f of n asymptotically less than log g of n, same relation f and g also. But if f of n, log f of n and log g of n if asymptotically equal, then f and g may not be equal. f and g may not be equal. For example, f of n is n square, f of n is n square, okay, and g of n is n cube. So f of n, g of n not asymptotically equal, f of n, g of n not asymptotically equal, but log f of n means log n square is 2 log n and log g of n log n cube is 3 log n, both are asymptotically equal, right. So now similarly one more statement also we can say, okay. So for example, if f of n is asymptotically smaller than g of n, if f of n is asymptotically smaller than g of n, okay, so then okay, log f of n can be asymptotically smaller than log g of n, log f of n can be asymptotically smaller than log g of n, otherwise log f of n can become asymptotically equal to log g of n, log f of n can become asymptotically equal to log g of n, okay. F of n asymptotically smaller than g of n, log f of n can remains asymptotically smaller than log g of n, otherwise log f of n can become asymptotically equal to log g of n. For example, n square and n cube, n square less than n cube asymptotically, but log n square log n cube asymptotically equal, okay. So if you take other example, f of n is n square, f of n is n square, g of n is 2 power n, g of n is 2 power n, n square less than 2 power n, but log n square and log 2 power n is also asymptotically smaller, okay. But if f is asymptotically equal, guaranteed log f and log g is also asymptotically equal, okay. So that just go through these 4 points, so which you already might studied, okay. Based on this we will solve next question. Right, is it okay? Any more explanation required for any of them? Right. Okay, solve this question. Which of the following statement is or true? Which of the following statement is or true? If f of n less than g of n, if f of n asymptotically smaller than g of n, f of n asymptotically smaller than g of n, okay. If you compare with the logarithmics, okay, so log f of n can be asymptotically smaller than log g of n, log f of n can be asymptotically smaller than log g of n, okay. So otherwise log f of n can become asymptotically equal also, okay. Depends on the example function, not guaranteed asymptotically smaller only, okay. Right. Nikhil Pandey AC, Chakravarti AC, okay. So 2 power f of n big O of 2 power g of n. Okay, see 2 power f of n asymptotically less than equal to 2 power g of n. 2 power big O asymptotically less than equal to 2 power g of n. Okay, then f of n also asymptotically smaller than g of n is the statement. Okay, if 2 power f of n asymptotically equal to 2 power g of n, because the function variable part in the power side, okay, 2 power f of n asymptotically equal to 2 power g of n, the guaranteed f should be equal to g only. Okay, because power side even constant multiplication is extra, okay, still is okay, otherwise you can apply logarithmic. Okay, so log 2 power f of n log 2 power g of n, okay, versus f of n and g of n. Okay, so sorry, if you apply logarithmic here, f of n less than equal to log f of n less than equal to log g of n. If log f of n less than equal to log g of n and f of n is also less than equal to g of n, the first statement is true. Okay, the second statement, if f of n big O of g of n, f of n big O of g of n means f of n asymptotically smaller or equal to g of n, f of n asymptotically smaller or equal to g of n, then okay, then 2 power f of n also asymptotically smaller or equal to 2 power g of n is the statement. Okay, the first statement is true, and see this one. See, f and g can possible to have asymptotically equal. F and g can possible to have asymptotically equal. Big O is allowed for asymptotically equal. In case f of n constant time bigger than g of n, in case f of n constant time bigger than g of n, still this statement is true. But that constant, if go to power side, that constant bigger is goes to power side, is not asymptotically equal. It mean to say, for example, f of n is okay, let's assume some 5n, g of n is n. Okay, f of n constant time bigger than the g of n. So in this case, okay, so 5n asymptotically less than equal to n is true. 5n asymptotically less than equal to n is true. Okay, that means, but 2 power 5n asymptotically less than equal to 2 power n is false. Okay, so this statement is false. Okay, right, second statement is false. The third one, f of n less than equal to g of n, f of n less than equal to g of n, log f of n also less than equal to log g of n. Actually this third and first is equal statements. Okay, so 2 power f of n instead of 2 power f of n, log of 2 power f of n, okay, is log of 2 power g of n. This f of n is become log f of n, g of n is become log g of n. This is log g of n. Okay, so g has to be there here. Okay, log g of n. Okay, now so f of n asymptotically less than equal to g of n, f of n asymptotically less than equal to g of n, their logarithmic is also same. Okay, but again this we already discussed this fourth option in the above note. Okay, log f of n asymptotically less than equal to log g of n. Okay, in case log f of n, okay, log f of n asymptotically less than equal to log g of n. Okay, then f of n asymptotically less than equal to g of n is true or false. Okay, less than equal to g of n is true or false, right? So see, log f of n can become asymptotically equal to log g of n. For example, okay, so this log f of n, okay, so is something like 4 times okay log n, 4 times log n. Log g of n is something like, so only log n, okay, only log n, okay. So that means f of n, assume that n power 4, f of n, assume that n power 4, okay. So log n power 4 asymptotically less than equal to log n, okay. So f of n power 4 and g of n, assume that f of n power 4, okay, g of n, assume that, okay. Log n power 4 asymptotically less than equal to log n is true, okay, because equality is satisfied here, but n power 4 asymptotically less than equal to n is false, okay. So this statement is also false statement. So the correct answer to this given question is A and C. How much score considered as good in OTS? Okay, so how much score considered as good in OTS is depends on, so in MEDISI test series, okay, in MEDISI test series, so if you get, okay, whatever the marks you will get, almost proportionally similar marks in the final exam, okay, proportionally more or less 5 more or 5 less, okay, depends, okay. So means overall if you take all FSTs of the MEDISI average, overall if you take all FSTs basic 4 and advanced 4, average of all 8 FSTs plus 4 marks, okay, if you completed, okay, on average whatever the marks you will get, so close number of marks you will get the final exam also, okay. So because in FST of MEDISI, so almost not only this year, in previous years also, okay, many of the students who secured top ranks, whatever the marks they scored in the final exam, sometimes they scored little higher than the MEDISI test series also, okay, right. So we'll conclude these notations, and go to the next topic with this question. So how many of given functions are exponential functions? Okay, how many of given functions are exponential functions? Okay, write given functions asymptotic increasing order. Write given functions asymptotic increasing order. This is first one and second one and third one, fourth one and fifth one and sixth one, okay, because in chart box it is become easier to write the increasing order, okay. So write these functions in asymptotic increasing order. see, so to prove it is exponential, okay, we should prove that log f of n, okay, should be asymptotically greater than log n. Log f of n should be asymptotically greater than log n. Okay, we can say f of n is exponential function. Okay, f of n exponential. Okay, if and only if log f of n asymptotically greater than log n. Okay, so if log f of n asymptotically less than equal to log n, then polynomial bounded. Okay, f of n polynomial bounded means less than equal to polynomial function. Okay, polynomial bounded. Okay, less than equal to polynomial function, not exponential. Okay, if and only if log f of n asymptotically not greater than log n, means less than equal to log n. If log f of n asymptotically less than equal to log n, then it is polynomially bounded. If it is asymptotically greater than log n, then exponential bounded. Okay, so now if you see this one, log n factorial, okay, apply logarithmic. So log n factorial is become n log n. Log n factorial is n log n. Okay, logarithmic, if you apply logarithmic, log n factorial is n log n. Okay, so log of n factorial is n log n, which is asymptotically greater than log n, okay, that means it is exponential function. Okay, this one is the exponential function. Then log of n factorial, if you apply logarithmic, okay, log of n factorial if you apply logarithmic, okay, log n whole factorial, right, sorry, log n whole factorial, if you apply logarithmic, okay, this value is log n multiplied with log log n. Okay, log n multiplied with log n, because log of n factorial and n log n asymptotically equal. Log of n factorial and n log n asymptotically equal. So these are the, okay, three things we are using to solve this problem. Okay, so now, so this is also asymptotically greater than log n. Okay, after applying logarithmic, it is becomes log n multiplied with log n, log n multiplied with log n times bigger than log n, log n times bigger than log n is also asymptotically greater than log n. Okay, so it is also exponential function. Okay, now if you apply logarithmic to this one, it becomes, okay, log of log n whole factorial, it becomes log n, okay, log n multiplied with log n, log n multiplied with log n. Okay, so log n multiplied with log n is asymptotically smaller than log n. Okay, log n multiplied with log n is asymptotically smaller than log n. So it is not exponential. Polynomial bounded. Okay, not exponential function. Okay, if you apply logarithmic to this one, log n multiplied with log n, if you apply logarithmic to this one, so log n multiplied with, so log n, right? Okay, it is also asymptotically greater than log n. Okay, this above function also asymptotically greater than log n. So log n times log n times bigger than log n. So it is also exponential function. This is also exponential function. Okay, but if you apply logarithmic to this function, it is becomes log n multiplied with log n. Apply logarithmic to this function, log n multiplied with log n means log n whole square. Okay, it is asymptotically smaller than log n. This function asymptotically smaller than log n. Okay, so it is not exponential function. Okay, this is not exponential function. So root n multiplied with log n, if you apply logarithmic to this one, root n multiplied with log n is asymptotically greater than log n. So asymptotically greater than log n means it is also exponential function. So 1, 2, 3, 4 out of these 6 functions, 4 are exponential functions. Out of these 6 functions, 4 functions are exponential functions. Okay. So answer to this first question is 4. Right. So 3, 5, 4, 2, 6, 1 is given by Patak. Right. Now when it comes to the second question, hope you first one is cleared. Okay, second question. So whoever exponential functions, those are asymptotically bigger than these remaining functions. Okay. So that means this log n whole factorial, okay, log n whole factorial is not exponential function, and log n to the power of log n is not exponential function. Okay, log n to the power of log n is not exponential function. So these two functions are asymptotically smaller than remaining 4 functions. Okay. So out of 4 functions, so see, so if you take the n to the power of root n versus n factorial, okay, if you apply logarithmic it is root n log n, if you apply logarithmic it is n log n. So n log n is bigger than root n log n, so n factorial is bigger than n power root n. Then what is other exponential function? So this is these two are done. Other exponential function, log n whole factorial. See, because n factorial asymptotically smaller than n power n, because n factorial asymptotically smaller than n power n, same thing also applicable for log n whole factorial, also asymptotically smaller than log n power log n. Okay, assume log n is m, n factorial less than n power m factorial less than m power m. Okay, so log n to the power of log n. So log n to the power of log n asymptotically bigger than log n whole factorial. Okay, so that means, so between these two log n whole factorial is asymptotically smaller than, okay, log n to the power of log n. See, this log n to the power of log n, so a to the power of log b base c can be write b to the power of log a base c, right? So this power side n, this log is interchanges. Okay, so log n to the power of log n is equal to the n to the power of log n, n to the power of log n. So this n to the power of log n, but it is log n to the power of log n. So if we interchange this base value, this is become n to the power of, okay, n to the power of log n. Okay, so this is also asymptotically, if this function is equal to like this, n to the power of log n, right? N to the power of log n, this function n to the power of log n. Okay, this function guaranteed asymptotically smaller than these two. Okay, so that means, so the out of these 4 functions, so n factorial is asymptotically bigger and n power root n is next smaller function, and this and other one is log n whole factorial. Okay, if you apply logarithmic to the log n whole factorial, log n multiplied with log n Okay, here if you apply logarithmic to this n to the power of root n multiplied with log n. So this is also asymptotically bigger than this. Okay, that means these two functions, okay, these two also exponential. Okay, so this one, right? Okay, these two also exponential. These two functions are asymptotically smaller than these two functions, right? Okay, now among these two, what is asymptotic increasing order? Among these two, what is asymptotic increasing order? If you apply logarithmic to this one, it is log n multiplied with log n. If you apply logarithmic to this one, okay, log n multiplied with log n. Okay, log n multiplied with log n. Okay, so log n multiplied with log n asymptotically smaller than log n multiplied with log n. So this function smaller than this function. So that means after this log n whole factorial next bigger function, log n whole factorial next bigger function, which is asymptotically smaller than, okay, log n whole power log n. Okay, log n whole power log n, which is asymptotically smaller than, okay, so log n whole factorial and log n to the power of log n. Okay, so log n to the power of log n. If you compare these two, okay, if you apply logarithmic, log n multiplied with log n, it is log n multiplied with log n. Okay, so this is smaller than this one, right? So the log n whole factorial, asymptotically smaller than log n to the power of log n. This is asymptotic increasing order. Okay, so asymptotic increasing order, log n whole factorial third function and log n to the power of log n. Okay, log n to the power of log n is fifth function, log n whole power log n is fourth function, log n whole factorial is second function. Okay, and the n to the power of root n is sixth function, log n factorial is first function. Okay, this is asymptotic increasing order of these six functions. Okay, so 3, 5, 4, 2, 6, 1, 3, 5, 4, 2, 6, 1, Satyam Kumar, Satyam Chakravarti, Patak, Sambhav. So very few are given correct answer. Right? Next see the loops complexities. Okay, so see this one, briefly revise before solving the problem. I is 1 to n, I equal to I plus 5. I is 1 to n, I equal to I plus 5. Print made easy. So this loop, whenever the constant to n, every time plus 5 is increment factor. This loop runs approximately n by 5 times. Okay, so the time complexity of this loop is order of n. Okay, just note before solving the problem. Okay, just note, it's not a problem here, just for note. N to 1 every time I decreased minus 5. Okay, this loop also approximately runs n by 5 times. Okay, this loop also approximately runs n by 5 times. Okay, so that means time complexity of this loop is order of n. Okay, and so I is 1 to n, I multiplied by 5. Every time I multiplication of 5. Okay, this loop approximately runs log n base 5 times. The time complexity is theta of log n. Asymptotic base value also not required. Okay, so while writing asymptotic notation, so every time I divide by 5, this loop also multiplication of 5 and divide by 5, this loop also approximately runs log n base 5 times. Okay, so the time complexity of this loop is theta of log n. Okay, so I is 10, I less than equal to n, I cube. This loop runs approximately, okay, log n log n, this base value is, okay, this inner base, this power side value is this outer base, okay. So time complexity also asymptotically equal to this one, okay. Similarly n to 1 cube root of I to the power of 1 by 3 cube root of n, this loop also runs log n times. Okay, so any doubt on this? Any doubt on this? Yeah. Right. So before solving problems of this, these are the three, these two are one category of the loops. Loop factor increment plus 5 or decrement minus 5, and the from 1 to n or n to 1, okay. These two are one category of the loops. The loop factor multiplication of constant or divide by constant, okay, either from 1 to n or n to 1, okay. And this third one is either 10 to some constant to n or n to constant. So I cube or cube root of n, the loop runs log n times, okay. So you can say it is one note, okay. If loop starts from 1 to n, okay, every time plus constant, or loop starts n to 1, loop runs from n to 1, every time minus constant, okay. These loops runs approximately n by c times. So time complexity we can say theta of n, okay. N to 1 to n every time I multiplied by constant, n to 1 every time I divide by constant, okay. These loops runs approximately log n base c times, okay. So then order of n under assumption if c constant, okay, if c constant order of n, otherwise you can say theta of n by c, okay. So now theta of log n, so time complexity of this one is become theta of log n base c. C constant if you say simply theta of log n, otherwise use that base as it is, okay. If loop runs from I is a to n, every time I power c, or n to a every time cube root of I, okay. These loops runs log n times, this inner base is this a and this outer base is this c. This initialized value is become inner base, this power value is become, okay, this outer log base, okay. So time complexity also theta of log n. Time complexity is theta of log n a and c, okay. If a and c constant you can ignore, otherwise if not constant you can say a and c as it is, okay. So these are the time complexities of various loops, okay. So this take it as a note, okay, take it as a screenshot and write in the short notes, okay. So take it as a screenshot and write in the short notes, okay. So most of the cases 80-90% of for loops time complexity, 80-90% of for loops time complexity you will able to handle just because of these three notes, okay. So this is not only completely solving session, okay, briefly revise the notes also, means briefly we are revising the things also, okay. So those who are already done, okay, so just make it as like it's a revision one more time, okay. So revising also, right? Now, okay, it is one of the PYQ question. It is one of the PYQ question. What is time complexity of this program? What is time complexity of this program? PYQ question. I think most of you are already done this one. So just recollect once again. Just resolve properly. Nishu Kumar, Satyam Chakrabarti, Nikhil Pandey, Uttam, Krish, right, very good. Okay, so it's a independent loops only, the inner loop not depending on the loop variable of outer loop. If it is independent loops, then find the frequency count of inner loop and find the frequency count of outer loop and multiply them is become time complexity. Find frequency count of inner loop and find frequency count of the outer loop means time complexity of individual loop. Okay, and multiply is become time complexity. J is 2 to n j square. J is 2 to n j square. So this is the third category. This is the third category of the loop. Okay, so this inner loop runs log n times. Okay, this inner loop runs log n times. The I is 1 to n I plus plus. Outer loop runs n times. Outer loop runs n times. So actual time complexity is theta of n log n. Time complexity is the theta of n log n. The inner loop j is 1, j less than equal to n, j square. Inner loop runs log n times, outer loop runs n times. Time complexity is multiplication of frequencies. So time complexity n log n. Okay, so but option is not in terms of n log n. He used k in the options. Okay, because he initializes n value equal to 2 power k. Okay, so this is correct answer only. You can say time complexity is n log n also. You can say time complexity is n log n also. But because n is initialized to 2 power k. N is initialized to 2 power k. So to get the means what is k value here? So to get the k value we need to apply logarithmic 2 times. So k is log n. Okay, k is log n. Okay, so because n value is initializes, you can write like this also time complexity. So you can write like this also, n is 2 power k, n is 2 power k, log n is k, but this option is also not available. Okay, so now what is other possibility? Leave n as it is, log n substitute as k, n and k. So all these are correct time complexities only. Okay, so the means n log n is not correct, k into log n is also not occur in any of the 3 cases, k square also not correct for any of the 3 cases, only one correct answer. Right, so this is also correct only, this is also correct only in case multiple selection one other option is given and it is also correct and it is also correct. Okay, all these are time complexities only. Okay, you can say time complexity n log 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 n, time complexity n log 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 n, where n equal to 2 power k, it mean to say, right. So small change I made to this PYQ question. Okay, small change to this PYQ question. So see this one. Okay, so P equal to 0 and Q equal to 0, I is 1 to n I plus plus, okay, outer loop, I is 1 to n I plus plus is outer loop, J is 1 to n to 1 J by 2, P is increases, okay, K is 1 to P, K multiplied by 2, Q is increases. Okay, so we are returning the Q. We are returning the Q. Which one is closely approximation return value of the program, and what is time complexity of the program? So he not mentioned about the K, previous question. So the Hamanta, so Nishu Kumar asking, so K is constant. Okay, he is not mentioned whether K is constant or not. Okay, in the question not given K is constant or not. So if constant, okay, also okay. So 2 power some constant is the n value. If not constant is also okay, because we are representing both the terms in the answer. Okay, so is not clearly given K is constant or not, right. Satyam Chakrabarti, Krish, Nikhil Pandey. Right. So Q initialized at 0, P initialized at 0. So outer loop I is 1 to n, I is 1 to n. Okay, so I plus plus. Okay, outer loop is running. The second loop J is 1 to n. Okay, J is n to 1. Every time J divide by 2. Every time J divide by 2. So this loop runs log n times exactly. Okay, so means approximately you can say plus 1 minus 1, that constant if you neglect. Okay, approximately log n base 2 times. Okay, the second loop runs log n base 2 times. Okay, so the P get increased log n base 2 times. Okay, log n base 2 times. Okay, so now let us see the Q value, estimated Q value. Okay, so let's expand the loop. I equal to I is 1, and anyhow it is only increasing the P. Okay, and based on the P, this second loop executes. Okay, K loop, this K loop executes based on the P value, and after that Q is get increased. So finally we need to know value of this Q. Okay, we need to know this value of this Q, right. So I is 1. Okay, I is 1. Okay, end of this loop, see P is increased at 0, Q is increased at 0, both are increased at 0. Okay, so this loop increases P value to log n. This loop increases P value to log n. So end of this loop P is become log n. approximately p is become log n, and the k value is becomes, okay, log p times executing this loop. Okay, this loop executing log p times. Okay, log p times this loop executing means p is log n here, log of log n times the third loop executing. Okay, then after that if I is becomes 2, already p is log n, it continues incrementing from the log n. From log n again log n increments happen. From log n already previous p value, again log n increments are happen. Now the new p value is double the, means a log n added to the previous value. That means log n plus log n, it is 2 log n. The new p value is if 2 log n, then this second loop, the q is increased log n times for I equal to 1. Q is increased log n times for I equal to 1. Okay. The second time the k loop, this k loop executes log of p times. That means log of 2 log n times. Okay. If this loop executed log of 2 log n times, okay, this q increases log of 2 log n compared to the previous q. Previously already q is log of log n, now the q is increased log of 2 log n times. Okay, plus 1 is added, these many times plus 1 is added. So by the time I equal to 1, q value become log n. By the time I equal to 2, q value become log n plus log of 2 log n. Okay, same thing is get repeats. If I equal to 3, already p is 2 log n, again it is executed increased log 2 times. Okay, that means end of this loop, okay, p value is becomes 3 log n. End of this loop, p value is becomes 3 log n. Okay, so that means this third loop log p times executes, log of 3 log n times this loop executes. Okay, log of 3 log n times this loop executes means it is becomes log of 3 log n times q get increased. Okay, the same scenario is repeats until I reach to n. Same scenario repeats until I reach to n. By the time I reach to n, p is become n log n. Okay, p is become n log n. Then the second loop executes log of n log n times. Second loop executes log of n log n times. Okay, and q increment also becomes log of n log n times. Right? Now we need to simplify this to get the q value. Okay, log n plus log 2 plus log n, log 3 plus log n, up to so on log n plus log n. Okay, there are n log n terms. Okay, there are n log n terms. Okay, log n plus log 2 plus log n, log 3 plus log n, log n plus log n, plus log 2, log 3 up to so on log n. Okay, so that means log 2 plus log 3 plus up to so on log n. Okay, this value is log 2 multiplied with, so this is the q value. This q value is becomes n log n plus log of 2 multiplied with 3 multiplied with up to so on multiplication of n. Okay, this is equal to n log n. Okay, n log n, and this is log of n factorial. Log of n factorial is become n log n. So and n log n and n log n, leading term is n log n. Leading term is n log n, right? So the q value, approximated q value is n log n. C. Then time complexity. See the number of times this innermost instruction executes. Number of times innermost instruction executes is also become time complexity. Okay. So this loop is executing n log n times. Okay. The second loop, these two loops are executing n log n times, and these loops are nested loops. These two nested loops are also executing n log n times. Okay. So this for I is 1 to n I plus plus. Okay, these two nested loop if you consider, okay, the time complexity is n log n plus n log n, okay, because of log n factorial. if you take these two loops, okay, I is 1 to n, okay, n times log n, it is become n log n, okay, overall asymptotic value is n log n only. So both are order of n log n. Right? Both are C. Okay, many are given D for this first one. Okay, so see, this is one of the PYQ question. This is one of the PYQ question. In examination, this P initialized here. Okay, in the gate examination, P initialized here. If P is initialized here, then every time this P value is log n only. Every time this P value is log n only, then the total summation become n log n. Okay, so but we are used this P initialization outside this outer loop. Okay, so that's why the approximated Q value is also n log n and time complexity is also n log n. How many full length tests should be given? So how many full length tests should be given? So see, means this is only, I think this is the first and 10th is exam. You have okay, so max to max 8 days in between. Okay, max to max 8 days in between. Okay, so now if I say 20 full length tests must be given and 15 full length tests must be given. Okay, or okay, these many full length tests must be given. Okay, so means if you done, then it is okay. If you not done, these 8 days you can't give 20 full length tests and 15 full length tests. Okay, so till 4th February, okay, till 4th February, okay, you can start give the daily one test at least. Till 4th February start give the daily one test. Okay, so from 5th to 9th, 5th February to 9th February, these, okay, 5 days. Okay, these 5 days revision of notes and briefly look the PYQ questions. Okay, revision of the notes, okay, short notes or whatever it may be. Okay, not every PYQ question, briefly look the PYQ question. Okay, so till 4th February from today. Okay, so one FST, at least you do one FST per day as per my idea. Okay, last 3-4 days stop writing the FSTs also, because you have only 8 days time now. So now I can't now it is not correct to say that you have to give 20 full syllabus tests or 15 full syllabus tests. If you are already given, that's well and good, but if not given also, if not given so many, you might have given 4, 5 or 3, 4 or depends. Okay, so next 4 days give 4 more tests, next including today. Next 4 days give 4 more tests. After that, okay, start revise the things and briefly look the PYQ important questions. Okay, so once again for the Q value, Praswal. Okay, so I just went little fast calculation because, okay, so I don't want you to wait long time. See, this is I think you cleared till this part. I think you cleared till this part. So by the time P is log n, okay, the third loop runs log n times. The third loop runs log n times, it increases log n. By the time P is 2 log n, the third loop runs log of 2 log n times, because third loop runs log P times. Okay, so log of 2 log n times this K loop. Okay, so then log of this one. Just expand, log n is first term, log 2 plus log n, log 3 plus log n, up to so on, log n plus log n. So here also one term log n, one term log n, one term log n, one term log n times log n. Okay, plus log 2, okay, plus log 3, okay, plus log n. Okay, so log 2 plus log 3 plus log n can be written log a plus log b is log a multiplied with b, log 2 multiplied with 3, log 2 multiplied with 3 multiplied up to so on n. Okay, this is log of n factorial. The second term becomes log of n factorial. Log of n factorial means n log n, asymptotically equal to n log n. log of n factorial asymptotically equal to n log n. Okay. So that's why the overall summation, so n times log n plus n log n times log n plus n log n, so the asymptotic value is n log n. Right. 40-50 marks in made easy full syllabus test. Okay. Still preparation not ends. Okay, 40-50 marks in made easy full syllabus test, still preparation not ends. Still you have, okay, so many times you are going to revise. Okay, so still not decide like you will get only 40 marks, only 45 marks only. Okay, still you have 10 days time. Okay, still give 4 more FSTs and keep revise and keep doing the PYQs. Okay, so still the preparation not completed, till you have to spend 10 more days for, okay, serious preparation. Okay, till game not over, right. Okay, so I am not exaggerating the things. Okay, so see, you will get the good college, anything 45 plus marks, 45 plus marks out of 100. Okay, so you will get the very decent college, good college. Okay, means say, so only, I am not saying that IISc IIT Mumbai for 45 marks. Okay, so for example IISc is there. Okay, I all 10, see, only IISc IIT Delhi, only these two colleges, 250 admissions are there. Okay, so MSc, including MSc, okay, MS and MSc in the IISc, 250 admissions are there for computer science. Okay, so like that old, so old IITs, all old IITs. Okay, if we include. Okay, so then, so I'm not writing ranking wise, that we can do post gate counseling, because okay, I'm just giving one statement to okay, get the confidence in the examination. Okay, so total 23 IITs are there, approximately 20 IITs almost giving good placements, maybe except 2-3 IITs. Okay, out of 23 IITs, approximately 2-3 IITs, okay, except 2-3 IITs, 20 IITs is okay, and the approximately so 10 to 15 NITs also giving very good placements. Okay, so and approximately, okay, 3 to 4 triple ITs, also giving very good placement, not ranking wise. Okay, I am just giving the list of colleges, means a possibility of colleges. Some universities like a Jadavpur University, okay, DTU, okay, so etc. This kind of universities also. If you think all these things, more than 40 to 50, more than 40 means 40-45 colleges, and every college, okay, on average, okay, so like a 100 admissions. Okay, on average 100, because computer science engineering and artificial intelligence or data science, or we can say information security or software engineering, various streams are there, right. So like 4,500 okay, admissions are there. Okay, so 4,500 means until AR 1 to AR 4,000, okay, still you will get the decent college. Okay, so where you will get average 20 plus lakh CTC job. Okay, so you can, okay, so it's not like only 2 colleges or 3 colleges and all. I am not saying that 45 marks, anything more than 45. Okay, anything more than 45 you will be in decent college, you will move forward in computer science. Okay, so like so remaining things you can take care in the next further higher education, means during MTech you can do whatever the research you want. Okay, Right, let's move to the next question. Okay, what is time complexity of the given program? What is time complexity of the given program? $1,200 to $1,500. So post gate counseling we can see $1,200 to $1,500 and which IIT and all, these all we can see post gate counseling. Okay, so now it is, let's not deviate with the college ranking and all. Okay, so post gate counseling, and we are always available in Telegram group of the Medici, so we'll discuss. Okay, but now your target is okay. So I am not saying 45, don't take me wrong. Okay, so like Ravi sir says that 45 marks is sufficient, nothing like that. I am saying anything more than 45, anything more than 45. If 50, 55, 60, 65, 70, 75, 80, 85 is up to you, up to your capability. Anything more than 45, approximately 50, assume that on average. Anything more than 50 marks is decent for your MTech admission. Okay, so not means, of course, okay, if you want IISc, IIT Mumbai, and you should get minimum to minimum 300 rank, because already 250 admissions na. So once upon a time, by the time we use it to give the gate examination, okay, so IISc, IIT Mumbai, very less admissions, 20, 25 like that. Okay, but now the only IIT IISc is 250 plus admissions. Okay, so anything more than 45, not like only 45, I am saying that 45 or more than 45, whatever the maximum marks you will able to achieve, okay, you will get the good college. Okay, so now if you are capable of 60 marks, okay, this 10 days in properly plan and make it 65 or 70. If you are capable of 70 and make it 75, and by properly planning this 10 days. Okay, so now if in case some are not studied so much, okay, so just at least think what are the subjects has to be revised and what are the subjects has to be done, so that at least I will get the 45 marks. Okay, so I am not saying that only for top 100 or 200 rankers. So some people might have studied 4-5 subjects. Okay, so now think how to revise this 10 days. Make sure that how to revise this 10 days, whatever the little small you studied so far. Okay, make utilize of them, make sure that it is 45 plus. Okay, maybe you join, or maybe you will take one more attempt, make sure you will get 45 plus. Okay, whatever little small you studied so far. Okay, you revise the things and utilize the as much as possibility. Okay, so like the means say right now even if you studied 4-5 subjects or 3-4 subjects, or some are maybe studied 8-9 subjects, some are might be completed all subjects, but few areas may left. Okay, so whatever left is okay, whatever little small you studied, make revise properly and do the PYQ, trust and make sure that you will able to cross not only qualified marks, at least 45 marks. Right. Then this one make fast. Nishikumar, yeah, time is very crucial. Yes, this 10 days utilize as much best as you can do. Okay, as much best as you can do utilize this 10 days. Okay, this 8 days, not even 10 days, 9 days approximately. Okay, so make sure you are going to be enhanced whatever the marks you are getting so far. Okay. Right. See, this is not completely independent loop and completely depending loop. See, this outer loop is independent. This outer loop is independent because the k value not used in second loop and k value not used in the third loop. Okay. So, outer loop is independent, but these two loops are depending loops. These two loops are depending loops, right. So, because I is 1 to n I plus plus, j is 1 to n, every time the increment factor of j is plus I. Increment factor of j is plus I. Okay. So, for these two loops to get the time complexity, we have to expand the loops. We have to expand the loops for the time complexity of these two loops. Okay. That cost can be multiplied time complexity of this because that one is independent. Because of this independent loop, whatever the frequency count of this outer loop, you can simply multiply, but we can't simply multiply second and third loop frequencies because third loop frequency is changing, third loop cost is changing based on the I value. I is also keep on increasing. Third loop cost is changing because of I value increment. Okay, because j is increased plus I times. Okay. So, now let us expand these two loops only, leave the outer loop, expand these two loops only. Okay. So, by the time I is 1, okay. So, the second loop runs, okay, 1 to n j is j plus 1, okay, 1 to n j is, okay, j plus 1, j is j plus 1 means the second loop runs n times. Okay, the second loop runs n times. If the second loop runs n times, the instruction x equal to x plus 1, the instruction x equal to x plus 1 executes n times. Okay, executes n times. Okay, frequency count is n. Okay, then after that, if I is becomes 2, the second loop j equal to 1 to n j plus 2, second time j equal to j plus 2. Okay, that means the second loop runs n by 2 times. Okay, the second loop runs n by 2 times, that means x equal to x plus 1 executes n by 2 times. Okay, frequency is added plus n by 2. Okay, and if I is becomes 3, now the third loop j equal to j plus I, j equal to 1 to n, j equal to j plus I is the increment factor. So, because j equal to j plus 3, the third loop runs n by 3 times. Okay, the third loop runs n by 3 times plus n by 3. Okay, plus n by 3. So, up to so on. If I is n, the third loop runs n by n times. Okay, so third loop runs n by n times, j equal to, okay, one time, n by n time means 1 by 1 time only. Okay, so j plus n, only one time the third loop executing. Okay, so for series purpose I am leaving as n by n. Okay, up to so on, the x equal to x plus 1 executes n by n times, means one time. Okay, that means if n is common, this series is 1 plus 1 by 2 plus 1 by 3 plus up to so on plus 1 by n. Okay, so this summation something like integral 1 by n. Okay, integral 1 by n is log n, right? Okay, so this summation 1 plus 1 by 2 plus 1 by 3 plus up to so on 1 by n is log n. Okay, that means this value is theta of n log n is the inner two loops cost. Okay, this inner two loops effective cost is, effective time complexity is theta of n log n. Okay, for this theta of n log n, and this outer loop cost has to be multiplied because outer loop is independent loop. Okay, so irrespective of the k value, the cost of second and third loop remains same. For next k value also the cost is n log n only. For next k value also the next two loops cost is n log n only. Now let us see the cost of this outer loop. Okay, this outer loop time complexity. Okay, So now the outer loop is running like this. K is initially 10. Okay. Next time it is become 10 plus n. Okay. Next time it is become 10 plus n. Okay. And plus n is added. Plus n is added every time. Okay. 10 plus 2n. Okay. Okay. The next time k value is become 10 plus 3n. Okay. Up to so on. Let's say 10 plus kn loop approximately runs k times. Okay, loop approximate, this k and this k is different, or otherwise 10 plus x times. Okay, so x multiplied with n. Okay, assume that this loop approximately runs x times. X times this loop is runs. We need to compute x value. To compute x value, so the 10 plus x times n, okay, should be less than equal to n power 10. Should be less than equal to n power 10. X times n less than equal to n power 10 minus 10. So x is estimatedly, okay, n power 10 minus 10 divided by n. Okay, that means asymptotic value is n power 9, right? Asymptotic value is n power 9. That means this outer loop runs, okay, outer loop time complexity of this outer loop, theta of n power 9. The second and third loop is n log n. So n power 9 multiplication of n log n. So overall time complexity is become n power 10 multiplied with log n. Okay, overall time complexity become n power 10 multiplied with log n. Right? Okay, so almost all are given A option. Okay, almost all are given A option. Okay, yes, equally given. Of course, B is also given. Okay, many people. Okay, last few comments are given A option. Okay, right. Yeah, outer loop we can calculate by using previous conditions. Outer loop we can calculate constant to n. Okay, plus constant means n by c we says. Okay, n power 10 by c value is n power 10 by n means n power 9. Outer loop runs n power 9 and these two loops runs n log n, and both are independent nested loops, means these two is independent with this outer loop. Okay, so now multiplication is the frequency, n power 10 multiplied with log n. Right? Clear this one? So now let us see some divide and conquer questions. Okay, so I am not explaining again basic merge sort and all, you all know that. So list with more than one element. Okay, divide the list into two sub problem. Okay, recursively sort low to mid and recursively sort mid plus 1 to high and combine the merge them. Okay, so time complexity of merging two sorted subproblems into single sorted subproblem is order of n times. Time complexity of merging is order of n times. Two subrecursions is called, it requires 2tn by 2 times. Okay, and the recursion t of n cost is becomes 2tn by 2 plus n. Okay, so now theta of n log n is the time complexity of merge sort. Okay, and extra space also required other than input array, extra space also we used. Okay, so other than input array extra space we used. I am not going details of the merge sort, so because you all know this, you all revised this. Okay, so this is the recursively dividing a problem into two equal subproblem. Okay, divide and recursively sort low to mid and mid plus 1 to high and merge the result. Okay, so merging cost to merge n by 2 elements and n by 2 elements. n by 2 elements and n by 2 elements of two subproblems, okay, which are already in sorted order, to merge into single sorted list. The time complexity of this merge is theta of n. Okay, I am not going in details of this algorithm with example and all, okay, so because you already studied this, right. Okay, now other possibility of the merge sort is called straight merge sort or non-recursive merge sort. Non-recursive merge sort, it is also called two-way merge sort. Okay, straight merge sort or non-recursive merge sort or two-way merge sort. Here what we do, so each element of the array considered as one sorted subproblem. Only one element of first element, second element, each element of the array is considered as one sorted subproblem and merge into single sorted two consecutive subproblems into one subproblem. That means this is two elements in sorted order. Two elements in sorted order. If for merging purpose, if x elements which are already in sorted order, okay, x elements which are already in sorted order and y elements also already in sorted order, okay, the y elements is also already in sorted order, the time complexity of merging into single sorted array, okay, time complexity of merging into single sorted array is merging cost x plus y. Okay, time complexity of merging into single sorted array, x elements and y elements already in sorted order, merge cost is x plus y, right. So this one element already in sorted, this one element already in sorted, merge cost is two elements, okay, sorry, merge cost is 1 plus 1. So the n subproblems, because two subproblems are merging into single list, two subproblems are merging into single list, it become n by 2 times we done the merging, n by 2 times we done the merging, and every merge, okay, x element and y element merge cost is x plus y, one element and one element merge cost is 1 plus 1, one merge is 2, okay. So that means n by 2 times we are done merging, this is one merge, this is one merge, total n by 2 times we are done merging. So one pass merge cost is n, okay, one pass merge cost is n. So this n lists become one list, n list become one list, for that it required log n passes, okay, log n passes required, okay. So log n passes, then n lists are become one list and each pass required n time. This straight merging, every pass will take the same cost, every pass will take the same cost. So n passes, each pass required n time, then time complexity of this two-way merging is also become n log n. Time complexity of the two-way merging is also become n log n. This basic thing already known to you, okay, that's why I am going little faster here, just to recollect the thing what you studied, okay. The n sorted list to become one single sorted list, n sorted list to become one single sorted list, log n passes required, okay. One pass n time, one pass n time, next pass also n time, next pass also n time. In this two-way merging, every pass will take the same time. Next pass, number of subproblems are reduces to off, merges are reduces to off, okay, but one merge cost is increases double, okay. That means this two elements and two element, now the merge cost is become 2 plus 2, that is 2 square, okay. So merge cost is 2 square, okay, is also become n, right. So this is the non-recursive merging or straight merging. Now the question is instead of n sorted lists, okay, n log k sorted lists, instead of n sorted list, n log k sorted list, instead of one element in each list, each list is already log n by k elements, each list is already log n by k elements, okay. So n log k sorted lists are there, every list log n by k elements are there, okay. So those n log k elements should be merged into single sorted list, okay. So what is time complexity to merge into single sorted list, okay, solve this problem. Keshav Sharma. Thank you. Is it fine? Is it fine everything? Now fine, right, thank you. Okay. Please like the video. Total should get minimum 100 likes. So it is not like formula, something like previous straight merge sort. Okay, something like previous question, straight merge sort concept should be used. The idea is okay, so total lists are n log k sorted supports are there. That means this is that instead of n elements here n times log k lists, n times log k sorted lists. Okay, and each list not single element, that means this is one sorted list. Okay, this is one sorted list. In this sorted list already log n by k elements are there. Okay, log n divided by k elements are already in the sorted order. Okay, next sub problem also log n by k elements already sorted order. Next sub problem log n by k elements already in sorted order. Okay, like that. Last sub problem, okay, log n by k elements already in sorted order. Log n by k elements already in sorted order, right? Okay, now like that, this is one sub problem, and this is second support, third sub problem support of the array, and like that n times n log k, right? Yeah, n log k sublists are there. N log k sublists are there. Each sublist n by log n elements already in sorted order. Okay, so a sorted subarray. Okay, so sorted subarray means these are already in the sorted order. Okay, the next log n by k elements already in sorted order. Okay, now this kind of merge means what we will do here, we will merge these two lists into one list, next two lists into one list, and next two lists into one list. We apply straight merging. Okay, we apply straight merging or two-way merging. Okay, so after next pass, okay, after next pass, see how simply we can solve this question. Very simply we can solve this question. So first you need to find time complexity for one pass. Okay, find time complexity of one pass. Okay, so same time complexity for next passes also for this two-way merging. Okay, how we will get time complexity for one pass? If x elements and y elements, time complexity of merging is x plus y. X elements and y elements, time complexity of merging is x plus y. Log n by k elements, log n by k elements. Here also log n by k elements. Log n by k elements, log n by k elements. Time complexity is, okay, 2 log n by k elements. Time complexity is 2 log n by k cost. Okay, size is also same thing. The result size is also same thing. Okay, so 2 log n divided by log n by k plus log n by k. 2 log n divided by k. Okay, so elements in the resulted list. Okay, and cost of merging is also same thing. Okay, now see this n log k lists are becomes half of them lists. Okay, that means n log k divided by 2 lists. N log k divided by 2 lists. That means n log k divided by 2 times we done the merging. Okay, so that how many mergings we done? N log k divided by 2 times we done the merging. Every merge takes 2 log n by k. Okay, every merge takes 2 log n divided by k. Right? 2 log n divided by k is the one merge cost. This 2 get cancel. So this is n log k log n divided by k. That means, okay, because k is not constant, so you have to use the k as it is. So that means n multiplied with log n is one term is there and log k is one term is there. Okay, and divide by k is also one term is there. This is time complexity of one pass. Okay, this is time complexity of one pass. Time complexity of one pass. Okay, next same time complexity for next pass, because this divide by 2 square, this multiplication of 2 square, divide by 2 cube, multiplication of 2 cube, same time for all passes. Okay, so number of passes, how many passes required? Number of passes. Okay, whatever the number of lists are there, number of lists are there, because two lists are merging into one list. Okay, so in each pass, okay, the passes are become log of the lists. Okay, so n log k lists are there, number of passes is become log of them. Okay, number of passes, okay, are becomes, okay, log of okay, number of lists in the first pass, number of lists in the first pass, right, that is n log k lists. This is become number of passes. This is become number of passes. This is time complexity of one pass. Okay, the total time complexity of merging, is theta of number of passes multiplied with this cost. Okay, so that means this is log of n log k, log of n log k is the number of passes multiplied with cost of one pass is n multiplied with log n multiplied with, okay, log k, n multiplied with log n multiplied with log k divided by k also. Okay, see which option is correct. Divide by k is there, other so first option also divide by k is there, second option no divide by k, definitely second is not correct. Log n and log n, log square n, of course it is given as it is. Okay, so n log n and log k multiplication is there, log of n log n directly given here. Okay, so C is the correct answer, right. Okay, Keshav, thank you. Understood, Nikhil, right. So whatever it is given, just to apply two-way merging, okay, by using two-way merge, okay, find time complexity for one pass. The good thing in two-way merge, all other passes also takes the same time complexity. Okay, because the next pass the number of lists are divided by 2, the cost of one merge is become multiplication of 2. So overall it is become same as the first pass. Okay, the number of passes is log of the number of input list, log of the number of input list. If n lists then log n passes, and log n list then log n passes, and so on. Okay, so now this is one of the PYQ question, one of the PYQ question. Okay, see m by k sublists, m by k sublists, okay, m by k sublists, each list of length k, each list of length k, okay, sorted using insertion sort, okay, and then merges using standard merge algorithm. Find time complexity of the algorithm. Options I didn't written. Okay, so but it's the same as the previous question. Okay, so now I'm just giving the hint, and will give the time to solve the problem. Okay, so like this there is log n. Okay, there is m by k subproblems. Number of subproblems are m by k, and one subproblem of length k elements. Okay, k elements in one subproblem. But the difference between this question and previous question, each sublist is already sorted in previous problem. Okay, each subproblem already sorted in previous subproblem. Okay, but here these k elements are not sorted. These k elements are not sorted. Like this first list is there, second list is there, up to so on m by k list is there, m by k list is there, and each list is not yet sorted order. Okay, and used insertion sort to sort the these k elements. Okay, this k elements sorted by using insertion sort, by using insertion sort. Okay, sorted these k elements. Okay, sort k elements. Same as the case for next k elements. Sort these k elements using insertion sort. Sort these k elements using insertion sort. Okay, after that apply the straight two-way merging. After that apply standard merge procedure. Then what is time complexity of this one? Okay, and also the repeat same question, and also repeat same question. Okay, so by using heap sort for each of these k elements instead of insertion sort, by using heap sort for each of these k elements. Okay, same question, use the heap sort here. BFS Prims Kushkal Thoda. Okay, we'll try, depends on the time you give. Okay, so if you able to stay back in the live, then definitely I will cover. I have a plan to cover almost all the areas, all the important areas. Prajwal Rawat, okay. Until last 3-4 days you can continue the FSTs. Until last 3-4 days means until 4th or 5th is the means beyond that means see last 1 day, last 2 days if you give the full syllabus test there is a problem like in case that test, because it's a test series is framed by one team of the people, in case unfortunately so many complicated questions in that test, okay, you will get lot of demotivation for the before just before exam, okay. So sometime what happens, okay, because many different teams is involved for the test series preparation, okay. So in case so 2-3 people one subject, one person one subject, one person one subject, in case in the test, okay, everyone is given complicated question, okay. So overall test is become too complicated, okay. In such case what happens, you may get the less marks in the overall exam of the FST, okay. If that is happening just 1 day before or 2 day before of your main exam, that may affect for your main exam. That's why, so don't give the FSTs from means mostly last 3-4 days, okay, don't give the FSTs before exam, okay. If you want to give full syllabus practice and give one PYQ test like a PYQ 2023 test, then you will not feel surprised because that is a PYQ. Most of the questions you might have already solved during the preparation, you will get the overall revision, okay. Right, okay. So insertion sort takes k-square time, insertion sort takes k-square time. One insertion sort, time complexity to sort these k elements, time complexity to sort k elements is k square. One insertion sort takes the k square time, okay. Then total m by k, so the m by k, okay, insertion sorts we done, m by k insertion sorts we done, m by k lists, okay, m by k lists, m by k times insertion sort we done, and each insertion sort takes k square times, okay. The overall cost of the insertion sorts, k and k get cancel is theta of m into k. Overall cost of insertion sort theta of m into k, right. After that we used standard merge procedure. Okay, then just we need to compute one pass cost. Okay, what is one pass cost? Time complexity of one pass. Okay, time complexity of one pass, the total, okay. So m by k lists na, half of the lists, that means m by, okay. So 2k lists, m by 2k lists in pass 1, these many merges are done in pass 1, and cost of one merge, this k elements and k elements, cost of this k elements plus k elements, okay, is 2k, cost of the k elements and k elements, this merge cost is 2k elements, okay. So m by 2k times we merges in the pass 1, cost is 2k, okay. That means overall cost of one pass is m, okay. Then number of passes, okay, next pass is also same cost, number of passes log of the number of lists, okay, number of passes is log of the number of lists, okay, for two-way merging, okay, number of passes is log of m by k, that means the standard merging takes m plus log of m by k cost is theta of okay, m log of m by k, and m passes we done, and so m multiplied with m is the cost of one pass, number of passes log of m by k, okay. Then already this is the insertion sort cost, and after that the standard merge, okay, after that the standard two-way merge we used, okay, standard two-way merge we used. Okay, the standard two-way merge is takes this much cost, order of m log of m by k, m log of m by k. Then overall time complexity is sum of these two. Okay, overall time complexity is sum of these two. So mk plus m log of m by k. Actually this one PYQ option is also given like this, big term only. Okay, now instead of using insertion sort, if I use heap sort, okay, so this heap sort cost only changes, so m by k times heap sort is done. Okay, m by k times, okay, heap sort applied for k elements each, okay. So k elements each heap sort cost is k log k, elements each heap sort cost is k log k multiplied with m by k, that means overall heap sort cost is become, okay, so m log n, this is m, right? K log k, sorry, heap sort cost k log k, by mistake I written log n here, k log k. Okay, right. Okay, so k and k get cancelled, m log k, because one heap sort of k elements required k log k time and repeated m by k times. Okay, and remaining the standard merge is same thing, okay. So standard two-way merging, it takes the same cost. Okay, so the second step is no difference. Okay, so now the total time complexity is becomes m log k plus, okay, m log of m by k, okay. So m log of m by k, log m minus log k, log of m by k, okay, m log m minus m log k and this plus m log k, okay. So is become m log m only. So this is m log k plus m log m minus m log k, so overall theta of m log m. Right. Okay, many are answered. Okay, Chaudhary, mostly you got 70. Okay. It's okay, that's what na, sometime more complicated questions, more tricky questions can be in one single FST. Okay, that's why I am saying that take the average of FSTs. Okay, don't worry if one FST is reduce the marks. If one FST is reduce the marks, it's fine. Okay, overall you should get the more marks. Okay, so hope you cleared this one. So quick sort, I am not explaining sorting algorithm, but briefly see. Okay, irrespective whatever the input, either input is ascending or input is descending or input is unsorted. Okay, the partition cost of the quicksort always order of n. Okay, so quicksort uses partition to divide the list. Okay, it chooses pivot element placed in correct position. Okay, whatever the input array is given, the partition cost is always order of n. The input is ascending order or input is descending order or input is unsorted order, the partition is always order of n only. But the time complexity of the quicksort is depending on how this partition is takes place. Okay, it is equal, two equal parts are more inputs in one side or less inputs in other side. Okay, or no input in one subproblem, all other inputs in other subproblem. Okay, the time complexity of quicksort is depending on the how this partition algorithm partitions the list. Okay, so I am not going details of the quicksort. I am not going details of the quicksort. Most of you already studied. Okay, so hope you understood. Okay, then worst case behavior. Assume that in this partitioning, assume that for every partition, if one list is no element, other list is all elements except the pivot. This partitioning is like this. Okay, so n elements of the input, after one partition, no elements one side, n minus 1 elements in other side, because anyhow pivot element is placed in correct position. If this is the way partitioning is done, then the quicksort leads to worst case time complexity. Okay, so the array of n elements which we used for quicksort, partition takes n time, but after one partition, no elements in one subproblem, n minus 1 elements in other subproblem, and this subproblem require t of n minus 1 time, and partition cost is n time and total cost is t of n. The recurrence relation become t of n minus 1 is the cost required for one subproblem and partition cost is n. The worst case time complexity become n square and maximum depth is become order of n. Maximum depth n reduced to n minus 1 input, reduced to n minus 2 input and so on. Maximum depth is become order of n and worst case is become n square. So this is one comparison for quicksort and merge sort. Okay, so for quicksort, okay, maximum depth is n levels. For quicksort, maximum depth is n levels. For merge sort, maximum depth is log n levels. Okay, so this is the worst case cost of the quicksort. MS means merge sort and QS is quicksort. Maximum depth of recursion of quicksort is n. Maximum depth of recursion for merge sort is log n. Okay, so when it behaves like a best case, for each partition, if each partition instead of no element and n minus 1 element, okay, if two equal subproblems, okay, pivotal after one partition, pivot element approximately placed at the mid position. If the list is divided into two equal subproblems, okay, then it is the best case time complexity. Quicksort behaves best case if each partition list divides into two equal parts. Okay, then t of n, two equal subproblems, each subproblem t of n by 2 time and partition cost is order of n, then time complexity become n log n, and that is a minimum depth of recursion is log n. Okay, so maximum depth of the recursion for the quicksort, is n and minimum depth of recursion for the quicksort is log n. Okay, maximum depth of recursion for merge sort or minimum depth of recursion for merge sort, both are log n only. Merge sort maximum and minimum both are log n, quicksort at least log n depth and at most n depth. Okay, so got it. Now average case analysis. Okay, so after each partition, neither like constant n minus constant or 0 n minus 0, okay, n minus 1, okay, nor like equal parts. N by 5 elements in one subproblem, assume 4n by 5 elements in other subproblem. Otherwise, n by 3 elements in one subproblem, the list divides into n by 3 elements in one subproblem which require t of n by 3 and t of 2n by 3 elements in other subproblem. Okay, and partition cost is n. Okay, neither not like a best case, not like a worst case, can considered as the average case analysis. Okay, so average case analysis can be considered. Okay, t of n, t of alpha n, this is the average case recurrence relation. T of n, t of alpha n, t of 1 minus alpha n. Okay, so alpha is in between 0 to 1. So this is also we can consider one of the average case recursion. Means if alpha is 1 by 2, then that is become best case. If alpha is 1 by 2, that is become best case. Okay, so the overall average case time complexity is also n log n. overall average case time complexity also n log n is the brief recollecting the quicksort and solve this problem. Okay, solve this problem. Okay, a median of the set of n elements is n by second smallest element. Suppose quicksort were always pivot is median value, quicksort pivot is median value. Okay, then what is worst case time complexity? What is worst case time complexity of the quicksort? This is the standard model question used to ask repeatedly. Okay, and one other question I am also displaying to save the time. Okay, so quicksort were always pivot random value, quicksort is always pivot random value. Okay, and what is the worst case of the time complexity of quicksort? Okay, Keshav previous question, that insertion sort performed one before beginning the straight two-way merging, before beginning the two-way merging we done insertion sort one step only, that is why we did not multiply. Every time we are not doing insertion sort for previous question. Okay. Write this one. Okay, so almost all are given correct answer. So if quicksort pivot element is median element, for example if you take the structure of the quicksort, median element is the pivot element. Okay, this is the quicksort idea. So before partitioning, okay, we just find the median element and then run the quicksort based on the median element. Okay, so that means, so choose the some median element and based on that median element we run the quicksort. Okay, so quicksort of low to high. Okay, this quicksort of low to high, we done the median identification of the array of n elements, median identification of the array of low to high, and based on that median, okay, based on that median, okay, quicksort is done. Assume median is a of k. Based on that median element partitioning is done. Okay, so okay, by using median of median algorithm, we can find median element in order of n time, estimatedly median element order of n time. Partition takes order of n time, because median element is a pivot element, the list guarantees divides into two equal parts. Okay, list guarantee divides into two equal parts. Okay, that means time complexity recurrence relation. Okay, time complexity recurrence relation. Okay, so 2 Tn by 2 because list dividing into two equal parts because of the median pivot, and selection of the median n time and pivot partition cost is n time. Overall it is n time only, order of n time only. Overall order of n time only. The time complexity is become order of n log n in all cases. Okay, this is for all cases, best case, worst case, average case. For all cases this much time required. Right? I hope you, most of you already know the quicksort. Even if it is random pivot selection, worst case is still n square only, because random, even if you go for random number, okay, still partitioning can be possible, no element one side and n minus 1 elements other side, okay, still partitioning can be done, okay, no elements one side n minus 1 elements other side, still this kind of partition possible, okay, still this kind of partitioning is possible. So the time complexity is become n square, okay, time complexity is become n square, right. So so overall so conclusion for divide and conquer, so just check it once, mud sort recurrence and depth of recursion, space complexity, okay, recurrence 2 equal parts n by 2 plus cn, okay, for quicksort best case recursion, worst case recursion, average case recursion, okay, minimum depth is log n and maximum depth is n, okay, best case log n and worst case n, okay, for the quicksort, okay. So now Max-Min algorithm, just take like a short notes, Max-Min algorithm, minimum n minus 1, 2n minus 2, 3n by 2 minus 1.5 comparisons, on average 3n by 2 minus 2, okay. So space complexity and time complexity, so binary search, go through it once, okay, binary search, okay, so recurrence and depth of recursion as well as, okay, time complexities and space complexities, okay. So fast exponential algorithm, all these are revised once, okay, so almost possible to get one question from this recursions and all, okay, almost possible to get one recursions and all, okay, because many are okay, so already known this topic I think so, so I am just skipping this one, okay, going to the next topic, okay. Okay, just go through it once, okay, write the proper notes later, okay, Sturgeon's matrix multiplication, Sturgeon's integer multiplication, okay, so complete short notes of the almost all examples of divide and conquer, okay. So let's move to the graph traversal topic, okay. So okay, which of the following statement is or true, okay. So DFS traversal directed graph, edges are, okay, tree edges, back edges, cross edges, forward edges and so on, okay. Just try this question. So those who want PDF in case, okay, so personally message to me, because in this, okay, so let me see, is it possible to add in YouTube, okay, in comment section I will add it, okay, in description, otherwise you can message in Telegram or WhatsApp. Okay. See, DFS traversal for directed graph, DFS traversal for directed graph. Okay. So all the four, these are the edge classification. DFS traversal for directed graph. Okay. Tree edges also, back edges also, cross edges also, forward edges also. Okay. So DFS traversal of directed graph. For example, if you do DFS traversal, assume this is the DFS spanning tree. Assume this is DFS spanning tree. Okay. So for some graph, DFS spanning tree for some graph. Okay. So these are the tree edges. Spanning tree edges are called tree edges. Okay. If there is no more further depth and backtrack and we explore other vertices, right? Okay. So there, if no more further edge and backtrack and visit other vertices, something like we do. Okay. So in DFS traversal, there may be a graph edge like this also. There may be a graph edge like this also, which is called back edge. Okay. There may be a graph edge like this, one path to other path. Okay. This is called cross edge. Okay. There may be other graph edge from parent to descendant. There may be other graph edge from parent to descendant. Okay. So the descendant to parent or parent to descendant. Okay. So back edge and forward edge. All four possible edges are possible for the DFS. Okay. But DFS traversal of undirected graph, only tree edges. Okay. Only tree edges and back edges. Okay. DFS traversal of undirected graph, only tree edges and back edges. Okay. So that means if it is undirected graph, okay, you will get these kind of edges only for DFS traversal. Assume this is DFS spanning tree. So all other edges of the tree is something like back edges. Okay. All other edges of the tree is something like back edge. Assume this is the DFS spanning tree. All other edges is something like this one. Okay. Remaining edge other than the tree edge is only back edge. Okay. For BFS traversal, other than the tree edges, remaining all edges are the cross edges. Okay. Other than the tree edges, remaining all edges are the cross edges, like this cross edges. Okay. So tree edges and cross edges. Okay. If it is a directed graph, forward edge is not possible. Okay. So it may become tree edge or it may become cross edge. Okay. This kind of cross edge is also possible. Okay. This is a directed graph traversal. Cross edge also possible, as well as back edge is also possible, but there is no chance to get the forward edge. Okay. So this is the edge classification. If any doubt or anything required explanation further with example, please post your comment. Okay. Anything further explanation required, please post your comment. Okay. So now what we are trying to say, DFS traversal of directed graph, all four edges are possible. Okay. All four edges are possible. Tree edges, back edges and cross edges and forward edges. Okay. BFS traversal of directed graph, forward edges not possible. Second one is false. DFS traversal of undirected graph. Okay. So tree edge, back edge only, it is also true. Okay. BFS traversal of undirected graph. Okay. So tree edge, back edge, there is no back edge for, okay, BFS undirected graph. Instead of back edge we get the cross edges. Okay. So this is also false statement, right? Okay. Now assume this is the given graph. If DFS traversal runs from vertex A, and adjacency selection during DFS traversal lexiographic order. That means, okay, so A adjacency is B, C, F. So first we need to choose the B, okay, and so on. Okay, lexiographic order. Okay, so now lexiographic order, and source vertex is also given, which is A. how many number of tree back cross forward edges respectively? Okay, do it. How many number of tree back cross forward edges respectively? Okay, so simultaneously, if those who are completed first one, and same question for the BFS also. Okay, this is one frequent model question, same question for the BFS also. Satyam, okay, so first apply the DFS traversal from A. Okay, write like a normal tree form, write like a normal tree form. Okay, A visited, A adjacent, B visited. Okay, so A adjacent, B visited, this is become tree edge. Okay, B adjacent, DFS traversal. Okay, DFS only na, yes. Okay, D adjacents, okay, E visited, D adjacent is E visited. Okay, and E adjacent F, G, H, but in geographic order, so F should be visit first, E adjacent F is visited. Okay, F adjacent G visited. Okay, so G is visited from F, and so G adjacent no one, and backtrack to F, no one, backtrack to E, from E adjacent, okay, so H is there, E adjacent H is there, from E visit the vertex H. Okay, now and from H also no unvisited edge. Okay, so backtrack to E, from E no one, and backtrack to B, and backtrack to A. Okay, from A C is next vertex we can visit. Okay, F is already done. Okay, so C is the next vertex visited from A, right? Okay, now from C D is visited. Okay, from C D is visited. This is DFS spanning tree. Okay, this is called DFS spanning tree. Okay, this is the DFS spanning tree. The remaining edges of the graph, is become tree edges, cross edges and forward edges. Back edges, cross edges and forward edges. So what are remaining edges? This D to H is become cross edge. Okay, so that means next one is H to Z, one edge is there. H is this path of the tree and G is this path of the tree. Okay, so H is not descendant or parent of G, vice versa. So H to G is also is become cross edge. These two cross edges, these two back edges, these two forward edges. Okay, so total 8 vertices, 8 only na, yeah, 7 cross tree edges. Okay, the number of tree edges are the 7, number of back edges are the 2, number of cross edges are the 2, number of forward edges are the 2. Right? Yeah, Satya Saudari, Devang, Satyam, Neeraj. Nishu Kumar, you only want 12 lakhs. If someone offers 15 lakhs, you will not accept that one. Okay. Nishu Kumar says that I don't want huge, I want only 12 lakhs package only. Okay. If someone offers 15 lakhs, 20 lakhs, you will not accept. Okay. Right. So, now run the BFS from the vertex A. BFS from the vertex A. A is a source vertex. A is a source vertex. A adjacencies has to be visit first. All these three are adjacent of A. All these three are adjacent of A. That is BCF. Okay. A adjacent B also. A adjacent C also. And A adjacent F also. Okay. So BCF, A visited and B visited and F visited and C visited. Then after that B adjacencies. B adjacency which is not visited is E. E is B adjacent. Okay. So from B, E is visited. Okay. Then C adjacent is D. C adjacent is D. Okay. Then D is visited. Then F adjacency is G. Okay. G is visited from F. Right. Now the E adjacencies are okay. So G is already done. G is already completed. So E adjacency is H. Okay. Right. H is adjacent of E. E adjacent is H. I think all vertices are get visited. So all 8 vertices are completed. Now see what are remaining edges. What are remaining edges of the graph? Okay. D to A. Okay. So D to A back edge. Okay. The D to A is become back edge. What is remaining edge here? F to B. Okay. F to B. F is here and B is here. F to B become cross edge. F to B become cross edge. E to F and E to G. Okay. E to F and E to G. Okay. So E to F is also cross edge and E to G is also cross edge. Okay. Now D to H and okay, where is D? D to H is also become cross edge. Okay. H to Z. Okay. H to Z. The H to G is also become cross edge. Okay. One back edge. 1, 2, 3, 4, 5. 5 cross edges. Okay. So one back edge, 5 cross edges, and forward edges definitely no one, and 3 edges are 7. So 8 plus 5. Okay. Right. So 7, 1, 5. 0. Right. So hope you done this one. Hope you done this one. So this is the one important model question. We need to calculate back edges, forward edges, 3 edges of the DFS traversal. Okay. So now see this one. This is very almost like a note. Okay. Almost this is one like a note. Okay. Even though some people already know this, but this is the very important question from the graph traversal. This is very important question from the graph traversal. Okay. So even though you already studied, please revise it again. Okay. So examination time, sometime easy thing also required to be revised multiple times. So silly mistake should not be done. Okay. So is there any possibility to forming cycle if cross edge is present but no back edge? Okay. So for DFS if back edge is there then only cyclic. For DFS traversal back edge is there then only cyclic. Okay. If BFS of undirected graph every cross edge is a cycle. BFS undirected graph, every cross edge is cycle. Okay, I will just go through it, go here. So in DFS traversal, okay, only because of back edge, the graph is cycle. Okay, either directed or undirected, only if back edge exists, okay, then the graph is cycle. This back edge exists, then graph is cycle. Okay, for DFS traversal, back edge is mandatory to prove graph is cyclic, either directed or undirected. Okay, but BFS traversal if you use, okay, every cross edge is one cycle. For undirected graph, every cross edge is one cycle. Okay, this cross edge one cycle, this cross edge one cycle and all. But for directed graph, if back edge is there, guaranteed cycle. Even back edge is not there, some set of cross edges can form the cycle. Okay, so cross edge may form the cycle. Okay, and back edge guaranteed form the cycle. Okay, so DFS traversal, only back edge is required, exists, then only graph cyclic. BFS traversal of undirected graph, if you prove cross edge is there, then cyclic. But directed graph of BFS traversal, okay, if back edge is guaranteed cycle. If back edge is not there, there may be a chance that set of cross edges can form the cycle. Because of that, for directed graph cycle detection, okay, better go for DFS algorithm. For directed graph cycle detection, better go for DFS algorithm, not BFS. Okay, so for undirected graph cycle detection, BFS or DFS, anything okay. Undirected graph cycle detection, BFS also okay, DFS also okay, right? Yeah, please do this one. This is very important question. Okay, so even though you know this answer, okay, please analyze one more time. Yes, DFS traversal. Okay, DFS traversal for directed graph. XS exploration begins, XE exploration ends. Okay, find correct order of starting and ending exploration for UV. Find correct order for starting and ending exploration for UV. Right? Yeah, target 100 likes. 6 more. Okay, Avinash says that ACD, Srishti says that ABD, hundred done. Now next target 110. Right. See, before means if you are already having explanation beginning and ending, it's okay, but those who are okay, so first time hearing this term, okay, so let me explain what is mean by exploration ending. So whenever vertex begins the traversing, whenever vertex begins the traversing or visits the vertex, then we say exploration begins. All their adjacency is completed, all their adjacency is completed and backtrack is also done, backtrack from that vertex is done, then exploration ends. Okay, so now if you take one sample graph, assume that this is the given graph, okay, given directed graph. Let us say this is the vertex A and B and C and D and E. Okay, if you apply DFS traversal, A assume A is a source, DFS traversal from A is a source. Okay, so A begins, you can visit B or you can visit C, any order, okay, any order you can visit. Okay, so let's assume, okay, this edge is also not there. Okay, even if you take B or D, any order is okay. Let's assume, okay, this, okay, this is the given graph, okay. So A begins the exploration, then B, if you visit the B, then B begins exploration, okay, then D begins exploration. That means we visited these sequence of edges, okay, A to B and B to D is visited. Okay, now D completed, no adjacencies left, then we say D ends the exploration and B ends the exploration, backtracks to A, B ends, okay, so back to B and no more unvisited, back to A. From A, okay, C begins the exploration, and then E begins the exploration, okay, and E is completed, backtrack to C, C is completed, backtrack to A, A is completed, like this. Okay, this is the traversing. Okay, A visited, after that B begins. Okay, so you can write like a tree form, not like B means you have to write like this only, you can write in a tree form to understand. Okay, then D begins, so A, B, D, and backtrack to A, okay, C visited and E visited, C visited and E visited. This is the DFS spanning tree. Okay, this is a DFS spanning tree. These are the spanning tree edges. Okay, so let's have some cross edge also. For example, this ABD already done. Then this graph edge is also there. This graph edge is also in the graph. Okay, this E to D is also one edge is there. Okay, so that it become cross edge. That means E to A is become back edge, this E to A is become back edge, and D to A, okay, this D to A is also become back edge. Okay, now E to D is become cross edge. Okay, E to D is become cross edge. Okay, so then forward edge, in case there is a edge from A to D also in the graph, there is a edge from A to D also in the graph, then that is become forward edge. Okay, now if the UV is back edge, okay, this is U, this is the U, and this is V. If UV is back edge, okay, UV, this U to V is a back edge. Who is begins exploration first? Okay, A begins, and after that D begins, D completed, then after that A completed. Okay, that means if UV is back edge, okay, if UV is the back edge, okay, so that means this back edge is the UV, this U to V. That means V should be start first. This A is started, after that D is started, A is started, after that D is started. First D ends, then A ends. Okay, A started, D started, D ends and A ends. That means V started, then U started, U ends and V ends, correct only. Okay, this is the exploration beginning and ending sequence, right? Now the UV is tree edge. If this tree edge is UV, then A started, then B started, B ends and A ends. Okay, so then UV is a tree edge, U should be start first, then V starts. Okay, then after that V ends and backtrack to U ends. Okay, it is also correct sequence. Okay, it is also correct sequence. If UV is cross edge, this cross edge is the UV. Okay, if this cross edge is the UV, see this path is already completed, means D is already begins and ends. D is already begins and ends. Okay, so for example E to D, this is, see, the E is begins, E started and end, this is ES, by mistake I written ES. E begins and ends. Okay, E begins and ends. Okay, D begins and ends, and after that E begins and E ends. Okay, so D begins and ends first, then E begins and ends first, that the edge is U to V. Okay, that means V should complete first, backtrack, and then U completed. Okay, so begins and ending is also correct sequence. So tree edge and forward edge is same sequence of beginning and ending exploration. Okay, so you will get the same thing. So all these are correct statement. This is not about the just answer to the question. You should understand this edge classification of, okay, each edge of the back edge, tree edge, cross edge, forward edge of DFS traversal of the directed graph. Okay, so one it's like a 4 different questions. Okay, it's something like 4 different questions. Each question can be, okay, framed, each option can be framed one separate question. Okay, so for this answer is all the options, but not about answer to this question. It is something like one note. Okay, it is something like one note. Okay, edge classification of DFS directed graph. If back edge, this is the sequence. If tree edge, this is the sequence. Cross edge, this is the sequence. Forward edge, this is the sequence. Simple thing is take some sample graph. Take some sample graph and see the simple sample graph. Okay, so easily you will able to understand exploration beginning and ending, and you will easily will able to get this sequence. Okay, right? Now, so how many biconnected components in the graph? Okay, how many biconnected components in the given graph? Make it fast. Sarath, I didn't understand what you mean to ask. F2B cross edge. Okay, so it is F2B. Okay, so recollect the definition. So cut vertex are also called articulation point. Cut vertex, or we can say articulation point. Okay, removal of vertex should disconnect the graph. Removal of vertex disconnect the graph. Such a vertex is called cut vertex. Okay, so for example, this is the graph. Okay, this is the graph. Okay, so this kind of vertex is called cut vertex. Okay, this kind of vertex is called cut vertex. Removal of this vertex disconnecting the graph. Okay, that is also called articulation point, is one thing. And second thing, if no cut vertex in the graph, then complete graph is one biconnected component. Okay, so graph G is single biconnected component. Graph G, single biconnected component. Biconnected component if and only if no cut vertex. If and only if no cut vertex. Okay, is the second statement. For example, if no cut vertex, then single biconnected component. For example, no single vertex removal is disconnecting the graph. No single vertex removal is disconnecting the graph. If you take this graph, okay, there is no cut vertex. Okay, this kind of graph is called, okay, single biconnected component. Single biconnected component. Okay, so then, so third one, if k cut vertices in the graph, if G consists k cut vertices, then okay, at least k plus 1 biconnected components. At least k plus 1 biconnected components in the graph, means not single biconnected component. Okay, if one cut vertex, at least 2 biconnected components. If 2 cut vertices, at least 3 biconnected component. These 3 are may possible for theoretical questions also. Okay, so meaning of cut vertex and meaning of single biconnected component, if G has k cut vertices and at least k plus 1 biconnected components. Okay, so it is also a regular question. Okay, so 4 is the one cut vertex, removal of this disconnect the graph. 5 is one cut vertex and 6 is one cut vertex and 7 is the cut vertex and also 13 is the cut vertex. Okay, so that means total 5 cut vertices. 5 cut vertices means should have at least 6 biconnected components. Okay, should have at least 6 biconnected components in the graph. 5 cut vertices means at least should be have a 6 biconnected components. Okay, so this subgraph with no cut vertex. Okay, maximal subgraph with no cut vertex. Maximal subgraph with no cut vertex is one biconnected component. Okay, this is one biconnected component, no cut vertex between 4 5. Maximum subgraph is this edge, and this subgraph is no cut vertex. Okay, this is other maximal subgraph with no cut vertex, and these 3 vertices is one biconnected component, and these 2 vertices is one biconnected component, and these 3 vertices is one biconnected component, and 7 9 one biconnected component, and 7 10 one biconnected component. Okay, so these are the different biconnected components. One biconnected component, this is second one and third one, and these 3 is the fourth one, and this is fifth one. Okay, and 6th, 7th, 8th, 9th. Total 9 biconnected components in the graph. Total 9 biconnected components in the graph, right? Hope you cleared this one. Okay. Next one more important thing is strongly connected components. How to see biconnected component or not? Biconnected component or not? This concept is only used for undirected graph. Okay. So undirected graph. Okay. So whenever they say biconnected component or connected component, it is undirected graph. Okay. So then if it is a directed graph, we don't call biconnected component. Okay. There we call it as a strongly connected component. Okay. Strongly connected component. Strongly connected component means maximal subgraph such that path from every pair of vertices in both the ways. Okay. Path from, okay, I to j also should be there and j to I also should be there. I to j should be there and j to I should be there for every pair of vertices. Okay, for every pair of vertices. For every pair of vertices there exists path from I to j and j to I. Okay, then we call it as one strongly connected component. The entire graph can be single strongly connected component. Entire graph can be single strongly connected component. Okay, if all the vertices of the graph there is a edge from both the ways. Okay, if entire graph is not single strongly connected component, then how many strongly connected components in the graph? Okay, now so for this, see, biconnected component better directly solve it instead of using algo. Okay, but whenever you take question related to strongly connected component, instead of applying hit and trial or instead of applying like a iterative procedure, okay, so better use the algorithm because of the edges in anywhere to anywhere. So it may leads to confusions. It may leads to confusion. Okay, so that's why what we are trying to do, we are using proper procedure. We are using proper procedure whenever it is counting of strongly connected component. Okay, so procedure to find the number of strongly connected component. Procedure to find the number of strongly connected component. Call DFS algorithm for given graph. Call DFS algorithm for given graph. Store vertices exploration completion order in the stack. Okay, we are saying now vertex exploration ends. Okay, like a D ends, B ends, okay, E ends, C ends, A ends. This vertex exploration completion order, okay, insert into the stack, push into the stack. Okay, so call DFS for from any source. Okay, so store vertex exploration completion order in stack. Okay, is the first step for counting the number of strongly connected component. Then construct the transpose graph. Construct the transpose graph. It means that I to j, okay, I comma j, edge of G, I comma j, this edge of G becomes, okay, becomes j comma I edge. Direction of the edge changes in G transpose. Okay, so compute the transpose graph. Okay, after computing the transpose graph, okay, call DFS for transpose graph. Call DFS for transpose graph by using top of stack. We are inserted in the stack na, by using top of stack as, okay, so source vertex. Number of DFS calls required to cover all vertices of DFS D transpose. Number of times DFS is runs to cover every vertex of G transpose, okay, is become number of strongly connected components of the given graph. Number of strongly connected components of the given graph is the procedure. Okay, call DFS vertex exploration completion order store in the stack and construct transpose graph and number of times G transpose. Okay, so required to cover the number of times DFS calls required to cover the G transpose is number of strongly connected components of the graph. While we are running the third step, source is top of the stack. Source is top of the stack, so which is not visited so far. Okay. Now the question is, how many number of strongly connected components in the graph? How many number of strongly connected components in the graph? Do it fast. Right. Okay, I see this one. So call DFS from any source. Okay, so any source no matter. Okay, you can start the DFS traversal from anywhere. Okay, so store vertex exploration completion order in the stack. Okay, store vertex exploration completion order in the stack. Okay, so for example, if you start the DFS traversal from vertex 1, okay, so like assume that 1 starts, then 1 adjacent is 5 starts and 5 adjacent is 9 starts. Okay, but no one else is there na. 1 visited, 1 adjacent is, okay, 5 visited. Okay, so 5 adjacent is 9 visited, no adjacents is, now 9 ends, then 5 ends, then 1 ends. That means, so 9 completed exploration, 5 completed exploration, 1 completed exploration, and now this DFS is completed. Okay, so because no adjacent for 9 and 5 and 1 which are left for visiting. Okay, next, even if you start from 2, it covers only vertex 2. Okay, let's say start from that 6. You can start anywhere. If you start from 2 starts and 2 ends. Okay, because 2 adjacent is 1 already completed. Okay, so instead of those many calls, okay, so I'm just using from here. This graph is already completed. Now 6 starts the exploration. 6 adjacent is 2 begins, and 2 ends also, because 2 adjacent is no one, 2 completed. Then back to 6 adjacent is 7. Okay, 7 starts, and 7 adjacent is 3. Okay, 3 starts. Okay, 3 adjacent is 4. Okay, 4 starts. 4 adjacent is 8. Okay, 8 starts. 8 adjacent is 12. Okay, 12 starts. Okay, then backtrack. So 8 adjacents are done. and backtrack till what? 7th position. Okay, so backtrack means 12 ends. Okay, 12 ends, after that 8 ends, after that 4 ends, right? Okay, so 4 ends. Okay, after that 3 is also ends, 3 ends, and after that 7, from 7 10 begins. Okay, 10 starts and 11, so from 7 11 begins, 11 starts and 10 starts, then 10 ends and 11 ends. Okay, so backtrack to 11 ends. Okay, then after that backtrack to 7 ends, and then 6 ends. Right, this is the vertex exploration beginning ending, because 169 already done, 169 already done. Vertex exploration completion order store in the stack. Okay, 2 ends. Okay, then 12 ends, then 8 ends, 4 ends, 3 ends, 8 4 3. Okay, then 10 ends, 11 ends, 10 11, and 7 ends, 6 ends, 7 6. Okay, this is the vertex exploration completion order, right? Now compute the transverse graph. Okay, compute the transverse graph. Each edge of the given graph is become, okay, so each edge of this given graph is become opposite in direction. Okay, so each of edge is reverse their edge direction. Okay, so like assume this is become 1 to 2, and this is become 5 to 1, and 9 to 5, and 5 to 6, 9 to 10. Okay, so like this edge is, okay, so I am just changing the direction of the each edge of the given graph. If anything is missed, please post your comment. Right? Okay, is it fine? Now this is called transverse graph. This is called transverse graph. Now apply DFS for this transverse graph. Apply DFS for this transverse graph. Okay, from source as this unvisited vertex. Okay, this top of the stack. Okay, this top of the stack has become source vertex. Okay, this is a source vertex. Okay, okay, next 6 is the source. Okay, DFS of 6 we called, DFS of 6 adjacent, 10 visited, 10 adjacent, 11 visited. Okay, 11 adjacent, 7 visited, 7 adjacent, 8 visited, 8 adjacent, 4 visited, and 4 adjacent, 3 visited. Okay, 3 adjacent is no one, and backtrack to 4 and backtrack to 8, 8 adjacent also no one, and backtrack to 7 and 11 adjacent also no one, and 10 and 6. DFS of 6, 10 adjacents also no one, 6 adjacents also no one. DFS of 6 covers these vertices. What are vertices which are covers? 6 visited, 10 visited, okay, 11 visited, 7 visited, 8 visited, okay, 4 visited, and 3 visited. These vertices become one strong connected component of the graph. Okay, so for this given graph, okay, so 6 7 8 4 3, okay, these vertices become one strong connected component of the given graph. These vertices become one strong connected component of the given graph. This is the vertices of one strong connected component. Now these vertices already visited. If you next again run the DFS for remaining vertices, 7 already visited, 10 and 11, okay, is also already visited, 3 and 4 and 8, okay, already visited. Okay, then next 12. Now call DFS of 12. If you call DFS of 12, 12 adjacencies already visited. Okay, that means DFS of 12 covers only one vertex. DFS of 12 covers only one vertex 12. Okay, that means only this 12 is one strong connected component. Okay, then after that 2 adjacent 6 and 3 already visited. DFS of 2 covers only 2. Okay, so DFS of 2 covers only 2, right? So only 2 is become one strong connected component of the graph. Okay, now 2 is also done. So 1 adjacent is 2 already visited. DFS of 1 is also covers only 1. DFS of 1 also is only 1. Okay, only 1 is one strong connected component. Okay, then after that again pop. So 5 adjacent is already visited. Okay, 5 adjacent is already visited. DFS of 5 covers only 5. DFS of 5 covers only 5. Only 5 is one strong connected component. Okay, then after that top of the stack is 9. Call 9 DFS of 9. DFS of 9 is also covers only 9. Okay, because 9 adjacencies of G transpose already covered. Okay, so 1, 2, 3, 4, 5, 6. 6 strongly connected components. Out of that 5 strongly connected components with one vertex only, 1 strongly connected component with 7 vertices. Okay, so this is the way to compute number of strongly connected components of the directed graph. Okay. Mamnoon correct answer, Sagar correct answer, Diviz, okay, CN Marthan and Pratik 6, Satyam Akash, okay, Sonu Kumar, thank you so much, okay, Deepshika, thank you so much. Right? Okay. What is time complexity required? What is time complexity required to test simple undirected graph acyclic or not? Okay. Simple undirected graph. Okay. Acyclic or not, or cyclic or not, anything. Okay. Cycle exists or not, it mean to say. And N is number of vertices, E is number of edges, adjacency list representation, let us say adjacency list representation of graph is used. Okay, adjacency list representation of graph is used. Okay. First of all, how we will see undirected graph DFS traversal, if you prove back edge, undirected graph DFS traversal, if you prove back edge, for example this is A adjacent is not visited, A adjacent is not visited, we have to visit, and B adjacent not visited, we have to visit. For example, C adjacent is A, C adjacent is A which is already visited, C adjacent is A which is already visited but not parent of C, C adjacent already visited, I assume that this kind of edge is there, C adjacent already visited but not parent of C, then the graph is cyclic. Okay, So that means we call DFS like this. DFS of U is the vertex we are exploring, U is the vertex we are exploring, P is the parent. Okay, and we need to find adjacencies of U. Okay, we need to find adjacencies of U. If one of the adjacent okay is V, one of the adjacent is V which is already visited, okay, which is already visited before, assume that, and already visited before, and it is not equal to parent of U. Okay, so of course C adjacent B also, but B is also already visited, but it is a parent of C. Okay, so this C adjacent, U adjacent is V which is already visited, not unvisited vertex, and it is not equal to parent, and it is not equal to parent. Okay, if this scenario exists, this UV is cross edge, sorry, back edge, this UV is back edge, then graph is cyclic, is the logic, that is the logic we apply. It means that if we able to get the first cross edge, okay, not cross edge, back edge, if we able to get the one back edge, okay, then the algorithm traversing is completed. Okay, algorithm means we need not require to traverse the whole graph. Okay, in case the graph consists only n edges, order of n edges, less edges. In case graph consists less edges, okay, like this, very least number of edges are there, maybe slightly more than one. Okay, like this, assume that close to the n edges, assume edges are let us say order of n. Okay, edges are order of n, assume that for n vertices, okay, less number of edges. Okay, then traversing cost is, this traversing cost of the whole graph is order of n only, traversing cost of whole graph order of n only, n plus e. For example, even if you start from here, from this you will visit this, from this you will visit this, and from this you will visit this, and from this you will visit this. Okay, this adjacent is already visited but not parent of this vertex. Assume this is A, parent of B is A, and from B C visited, C parent is B, from C D visited, D parent is C, from D E visited, E parent is D, and E adjacent is A already visited and it is not equal to parent of D. Okay, then this is called cross edge, then this edge is the back edge, sorry, this edge is the back edge. So graph is a cyclic. Okay, now in case the graph has more edges, almost complete connected graph. Okay, graph has so many edges, almost complete connected graph, like assume that. Okay, so something like this, so many edges in the graph. Okay, it is almost like a complete connected graph. Assume that this is the other possible case, more edges in the graph. Okay, so many edges in the graph, may not be fully complete connected but almost complete connected graph. Now see how many vertices has to be traversed to get the back edge, to get the first cross edge, first back edge. This is visited, this from this, assume this vertex is visited. Okay, from this vertex is visited. Okay, A, and A adjacent is B visited, B adjacent is C visited. Now see here, C adjacent is A already visited but not parent of C. C adjacent is, because C parent is B, C adjacent is, okay, already visited but not parent of C. If you get this first back edge, then you already came to know cycle is there, then you will not require to traverse the remaining graph, then also become time complexity order of n. So that's why the only order of n time is sufficient for this example. Only order of n time sufficient for this example. Okay, please, all are given option A. Okay, option A means n plus e. N plus e means for this case it should require n square time. For this case it should require n square time. Here also it required order of n time. Okay, you will not require to cross more than n edges to get this back edge. Okay, if in case edges are less, you may require to traverse whole graph. But even if you traverse whole graph, edges are n only. So the time complexity become order of n only. If graph is complete connected graph, okay, means almost edges are n square, order of n square, n into n minus 1 by 2, close to n square edges, okay, order of n square edges. But you need not require to traverse whole graph to get the cycle. Okay, it will not take more than n time to traverse the graph. Okay, got it? Graph traversal only used, but time complexity not takes more. Okay, is this okay? Are you able to visualize why order of n only? Okay, almost all are given order of n plus e. Okay, it means complete graph traversal. Okay, two cases I explained. In case less edges, you may require to traverse whole graph. Okay, then also order of n only, because edges are less. In case if more edges, then you will traverse until you will get the first back edge. Then also order of n time. Okay, because you are not traversing whole graph, right? Sagar, Neeraj, Mamnoon Khan. Okay, clear this one, right? Now, so the algorithm I explained, same thing. Okay, so if adjacent is not visited, normally called DFS along with the parent. If adjacent is already visited, then we are testing that visited adjacent is parent not equal to parent. The U adjacent is V already visited but not equal to parent. Then graph is cyclic. Then we are terminating. Means not traversing remaining graph. Okay, not traversing remaining graph. Okay, yeah, if matrix given, that's the reason specially I mentioned this. If matrix given, adjacency matrix given, both the cases it becomes order of n square. Because okay, so even though less edges, we have to find adjacencies of A. If it is adjacency matrix representation, finding adjacency of one vertex is become order of n time. During finding adjacency of A, n time. During finding adjacency of B, C, D, E, n time. The time complexity of finding adjacency is mandatory. Even less edges or more edges. Okay, finding adjacency is mandatory. Okay, it takes order of degree of that vertex. Using adjacency list. It takes order of n time using adjacency matrix. In case it is adjacency matrix, best case is become n and worst case is become n square. Okay, got it? Now this is also adjacency list representation. What is time required? What is time complexity required to test given directed graph is cyclic or not? Okay, what is time complexity required to test given directed graph is cyclic or not? What is time complexity required to test given directed graph is cyclic or not? So difference between previous and this question, difference between previous and this question, it is directed graph. Directed graph cyclic or not? Right? Done this one? Yeah. Srishti, Mamnun Khan, Sagar, Dhruv, Neeraj, Avinash, Satyam. Check it again. Srishti correct. Srishti Gupta. Okay. So here again back edge is required of DFS traversal. Again back edge is required for DFS traversal. Okay. So but it's a directed graph, na? If it's a directed graph, if in case the graph consists less edges, okay, in case the graph consists less edges like this, okay, like this graph is there, assume that, then time complexity is become order of n, time complexity is become order of n, because edges are order of n, because edges of order of n. Because see, so now assume that we visited this vertex, this adjacent is visited, okay, this adjacent is visited and this adjacent is visited. Now, okay, so the adjacent of this already visited, okay, it's not like a parent and all, slightly different color of the vertex should be used, okay, like we call okay, white vertex, black vertex, gray vertex and something like some different logic is there, but we need to identify this first back edge. We need to identify this first back edge. To identify this first back edge, it required order of n time. Okay, so but so if you observe to form directed graph cyclic, okay, or acyclic, okay, to form directed graph acyclic, okay, so the graph can have at most, okay, at most n into n minus 1 by 2 edges, n into n minus 1 by edges, okay, at most n into n minus 1 by 2 edges, still can be acyclic, still G can be acyclic. Okay, so because total edges, okay, so number of edges, okay, okay, maximum number of edges in simple directed graph, of n vertices, okay, is n into n minus 1, double than undirected graph, n into n minus 1 edges. Okay, so the given directed graph can have at most n into n by n minus 1 by 2 edges, can have at most n into n minus 1 by 2 edges, still it can be acyclic. Okay, still it can be acyclic like this. See, 6 edges, still it can be acyclic. Okay, So more than that, more than n into n minus 1 by 2 edges in the directed graph, it can definitely become cyclic. Okay, if I feed this kind of graph, if I feed this kind of graph, okay, then there is no back edge, there is no back edge, has to be traverse all the graph, has to be traverse all the graph, and edges also not less, edges also not less. So the DFS traversing cost, okay, DFS traversing cost to detect the cycle or acyclic or not. Okay, so DFS traverse, okay, so to test acyclic or not, to test acyclic or not. Okay, required order of n plus e is become n square. Okay, now the time complexity is become order of n square, now the time complexity is become order of n square, still there is no back edges they exist. Okay, so got it. So in this way you may not able to complete in order of n time, you may not able to complete in order of n time if it is a directed graph cycle detection. Okay, because more than order of n into n minus 1 by 2 edges means order of n square edges, still it is acyclic. Order of n square edges still is acyclic. Okay, you are applying cycle detection for this graph, has to be traverse whole graph, has to be traverse whole graph, right? Is it clear? In that case time complexity become n square. Okay, so that's why better to say not n plus e, only not only order of n time, not only order of n time, you can say order of n plus e time by using adjacency list graph. Here also order of n plus e is fine because e is, okay, e is n edges only, order of n edges only, n plus e means order of n. So best case is become order of n only if edges are less, worst case is become order of n square if edges are more. Okay, so overall we can say order of n plus e. Okay, here one other important point we discussed, how many maximum possible edges in directed graph, how many maximum possible edges in directed graph, okay, which is still acyclic. Answer this question, how many maximum possible edges in directed graph, still it is acyclic graph. How many maximum possible edges in directed graph, still it is acyclic. How many maximum possible edges in directed graph, still graph is acyclic. Right, okay, maximum at most n into n minus 1 by 2 edges, still graph is acyclic. Okay, so means the for undirected graph maximum n into n minus 1 by 2 edges na undirected graph. Okay, each undirected graph can convert into directed graph with acyclic. Each undirected graph can convert into directed graph with acyclic. Okay, so maximum n into n minus 1 by 2 edges in the graph which can be still acyclic. Okay, so graph theory applications are very important for examination because see directed graph behaves one way, undirected graph behaves one way. Okay, so counting and time complexities, adjacency list, adjacency matrix, lot of importance is there for the graph algorithms. Okay, so I'm written algorithm but it's no time to explain this algorithm and all. Okay, so graph traversal is done, graph traversal is done, then MST questions will do MST questions is also very important. Okay, so now so start with one simple question. So start with one simple question. How many spanning trees possible for complete connected graph of 4 vertices? How many spanning trees possible for complete connected graph of 4 vertices? Okay, so complete connected graph of 4 vertices. Okay, so then second question, how many spanning trees possible for simple, okay, this graph, this given graph. Okay, very good. Sambhav, Sagar, Sonu, Shubham, Akash, second question, please try second question now. Please try second question now, make it fast. Neeraj 29 and Sonu 26. Okay, the first question, so it directly we can apply formula for this. First question, directly we can apply formula for this. Okay, so number of possible spanning trees, simple undirected complete connected graph with n vertices, n into n minus 2 spanning trees are possible. So it's a direct formula we can use. That means 4 times 4 to the power of 4 minus 2, total 16 spanning trees possible. Okay, 16 spanning trees possible for undirected graph complete connected with 4 vertices. Then this is the second question. How many spanning trees possible for this given graph? Number of possible spanning trees for this given graph. Okay, Sambhav Jain came to closest. Sambhav Jain came to closest. Okay, so next closest is Mamnoon Khan and okay, so far forest is 29. Sayan Chakravarti Prajwal, okay, very good. Okay, Sayan Chakravarti and Prajwal, very good. So very accurate. Okay, so it is not easy to solve this kind of question in first attempt. Okay, now see total 5 vertices and 1 2 3 4 5 6 7 edges. Okay, 7 edges are given. Out of 7 edges, okay, 3 edges required, 4 edges required for one spanning tree. Okay, so 4 edges required because 5 vertices are there. Okay, so spanning tree required 4 edges. Spanning tree required 4 edges, right? 4 edges required the spanning tree. Now the total possibility is 7C4 ways you can select. 7C4 ways you can select for 4 edges out of 7 edges. 7C4 selection, but not every possibility of 4 edges is the spanning tree. Not every possible 4 edges is the spanning tree. You have to eliminate the choices. You have to eliminate the choices of selection of the 4 edges from say 7 edges which are not spanning trees. Okay, so now see So out of four edges, okay, three edges forms the cycle. Out of four edges which we selected, three edges forms the cycle. One is outside that, means because total selection is four edges. One is remaining edge, either this edge or either this edge, okay, or either this edge, okay, or either this edge, something like that. For example, these three edges plus fourth edge can be anyone else, okay. So 1 2 3 4 other possibilities are there na. The fourth edge can be this one, or okay, fourth edge can be this one, okay, otherwise fourth edge can be this one, okay, otherwise the fourth edge can be this one, which is not spanning tree, okay. These three edges plus fourth edge, either this, okay. That means, okay, for this cycle ABC, okay, for this cycle ABC, these three edges plus fourth edge is one other, okay, fourth edge is one other edge. So that fourth edge can be this BD also, or this AD also, okay, or this CE also, or this DE also, okay. That means these are four choices which not spanning tree. Like that, see how many other possibilities of three cycles, three vertex cycle, okay. Same thing here, this three vertex is one cycle, okay. Fourth edge can be either this, which is not spanning tree, okay. So there are two possibilities of three vertex cycle, like the second possibility is, so ABD, okay, these three edges are selected plus fourth edge is one of other, okay. So fourth edge is one of other, either this edge or this edge or this edge or this edge, okay. So that means only two possibilities of three vertex cycles, 4 plus 4 means two possibilities of three vertex cycle. Each of these three vertex cycle, okay, fourth edge can be any one of the four possibilities, okay. 4 plus 4 8 possibilities is not spanning tree. Now also other possibility, all four vertices can form the cycle, all four edges can form the cycle. These are the three edge cycle plus fourth edge is outside, plus all four edges can form the cycle. What are possibilities of all four edges can form the cycle, okay. So this is four edges which is forming cycle, one cycle, okay. So this is four edges, okay, this is four edges which is form cycle, is not a spanning tree, okay. And also one more cycle is there, okay. This is four edges which is form cycle, okay, this one ACBDA, this is four edges cycle which is form cycle, okay. That means there are three cycles of four edges, of four edge length, three cycles of four edge, okay, four edges you can say, okay. So those three also not spanning trees, okay. So this 8 plus 3, 11 are the not spanning trees, okay. Those remaining is possibility of spanning trees. 7C4 is 35 minus 11 which is not spanning trees, 11 not spanning trees, the remaining 24 spanning trees possible. So it is topological ordering, okay. So it is directed graph na, there is no meaning to say topological ordering and all, okay. It's a directed graph, no meaning to say topological ordering and all. There is one way, there is a Kirchhoff theorem to find number of spanning trees, but in that theorem what it required to do, we have to find cofactor cofactor, if it is a 5 by 5 matrix, if it is a 5 vertices, we have to form adjacency matrix form of the 5 by 5, and so there is some procedure. In last step we need to find cofactor. Okay, so because 3 by 3 matrix, 4 by 4 matrix, okay, cofactor is okay, but beyond that cofactor takes so much time na. So that's why Kirchhoff theorem is also takes lot of time. Okay, so to find the number of spanning trees. Okay, so we are using the proper logic. We selected all the possible selection of 4 edges and removing every possibility of the cycle over the 4 edges or less than equal to 4 edges. Every possibility of the cycle, okay, less than equal to 4 edges. Okay. Yeah, the topological order is not applicable here. Okay, right. So this is the one thing. Next, second thing, the complete connected graph, connected undirected graph, complete connected undirected graph of 5 vertices having 10 edges, 5 vertices having 10 edges, edge weights are 1 2 3 4 5 6 7 8 9 10. Okay, minimum possible weight, okay, so maximum possible weight of minimal spanning tree, MST only. Okay, minimal spanning tree only, maximum weight of minimal spanning tree. Okay, minimal spanning tree, maximum cost. Okay. Likes. Okay, so the complete connected graph of 4 vertices, complete connected 5 vertices, sorry, complete connected graph of 5 vertices with 10 edges. Okay, so total 10 edges in the graph, undirected complete connected 4 vertices and 10 edges. Okay, see the all distinct edge weights are distinct. First mean cost edge guaranteed in the MST, first mean cost edge anywhere in the one can be anywhere in the graph. Okay, first mean cost edge guaranteed in MST, second mean cost also guaranteed in MST. Okay, because first mean cost and second mean cost may not form the cycle, first mean cost and second mean cost definitely not form the cycle because edges are distinct. Okay, so in this way the first minimum must be in MST, second minimum must be in MST, right, but third minimum may not. Okay, third minimum may not. Okay, may not in the MST. Okay, why? Because the third minimum can be here. If third minimum is here, it is not come into the MST. this vertex is not, this edge is not coming to the MST. Okay, so this first mean cost edge, this first mean cost edge can be in MST and the second mean cost edge can be in MST. Third mean cost edge may be form cycle with these two. In this way, if you think, third mean cost edge may not be in MST. Okay, in case if third minimum is not in MST, in case the third minimum is not in MST, for 3 vertex complete connected already done. For 3 vertex complete connected already done. Okay, then so this is the first minimum assuming here, for second minimum assuming here, and third minimum assuming here, it is not in MST because of cycle, right? Then fourth minimum, because third minimum not came to MST, the fourth minimum either adjacent to this one or adjacent to this one or adjacent to some other vertex or adjacent to some other vertex, fourth minimum beyond this cycle only. Fourth minimum beyond this cycle only, either this edge or this edge or this edge or this edge, any one of this edge if you take. Fourth minimum beyond the cycle only, because third minimum is excluded, guaranteed must be fourth minimum in MST. First minimum must be in MST, second minimum must be in MST, third minimum may not be in MST, maximum possibility where worst case we are talking about, but third minimum is discarded, we can't discard 1 and 2 because those are must be in MST, third minimum is discarded, fourth minimum guaranteed in MST if third minimum is eliminated. Okay, if third minimum not eliminated, third minimum in also in MST, fourth minimum may not be in MST. Okay, now after that the fifth minimum also can form cycle with these 4 vertices, sixth minimum also can form cycle with these 4 vertices. Okay, assume fifth minimum is here, it will not come in MST, next minimum is here, it will not come MST, means that there may be a possibility, third minimum is eliminated, fourth minimum is must, there can be a possibility these two may not be in MST. Okay, these two may not be in MST. Now complete connected of 4 vertices is completed, complete connected of 4 vertices, 6 edges is done. Okay, 7th edge, because 3, 5, 6 minimum, 3rd, 5th, 6th minimum is eliminated. Okay, if you take next edge, already 6 edges over, if you take next edge, either this edge or this edge or this edge or this edge, it is definitely in the MST. The next mean cost edge guaranteed in MST. So 7th minimum is in the MST. Okay, that means MST cost is become 1 plus 2, 3 plus 4, okay, 7 plus 7, okay, 14 is the maximum cost of minimal spanning tree. Okay, 14 is the maximal possible minimal MST cost, minimal spanning tree cost. Worst case minimal spanning tree cost can be 14 if edges of the graph 1 to 10, okay, edges of the graph 1 to 10, right? Yeah, almost all are given correct answer for this one. Okay, take Pratik. Okay. Now with this concept, okay, solve this question. Consider weighted graph G with distinct edge weights. Okay, weighted graph G with distinct edge weights. Otherwise undirected graph, weighted undirected graph. Okay, weighted undirected graph, okay, with distinct edge weights. Which of the statement is are true? Okay, first statement, okay, second mean cost edge of G must be in every MST. Third, either third mean cost edge or fourth mean cost edge or both of them must be in MST. The third statement, third mean cost edge if not in MST, then fourth mean cost edge must be in MST. Okay, then fourth one, okay, max cost edge of every cycle, max cost edge of every cycle of G, okay, excludes in every MST. Okay, max cost edge of the cycle is excludes in every MST. So if you clear the previous one, if you clear the previous example, okay, you should able to visualize this easily. Okay, see this one. Okay, either only third minimum or only fourth minimum. Okay, only third minimum or only fourth minimum, or both must be in every MST. One of these three cases must be in MST. Either only third minimum or only fourth minimum, or both of them must be in MST. True or false? Okay, this scenario is true for second and third. This scenario is true for second and third. Okay, so this scenario is true for second and third. Either second minimum or third minimum or both of them. Okay, either second minimum or third minimum or both of them, okay, must be in MST. Okay, must be in MST. What about third and fourth? What about this third and fourth? Okay, what about third and fourth? Okay, so one of them, okay, either third minimum or fourth minimum or both of them must be in MST. True or false? Okay, either third minimum or fourth minimum or both of them, okay, must be in MST. Means what you need to prove? Okay, is there any possibility minimal spanning tree without having third and fourth minimums? Is there any possibility minimal spanning tree without having third and fourth both of them? Okay, because eliminated false case is what? False case is what? Only third minimum but not fourth minimum is one true case. Only fourth minimum but not third minimum is second true case. Okay, both third and fourth minimum is third true case. Then what is false case for this? What is false case for this? If you prove that there is a MST which doesn't have third and fourth minimum for distinct edge weights. If there is a MST which doesn't have third and fourth minimum, is there any MST, okay, which doesn't have third and fourth minimum? Under assumption MST has more edges. Okay, if you take the graph with only 4 vertices, MST required 3 edges only, then OI need fourth minimum. Not like that. That is not the assumption. Assume that still fourth minimum you are taking na, still fourth minimum you are taking. Assume graph has more than 5 edges. Graph has more than 5 vertices. Okay, n is more than 5 vertices. Okay, don't take like a simple small graph. Okay, if graph with only 4 vertices, then I need only 3 edges. We need the fourth minimum edge and all, nothing like that. I am assuming that we have the more edges required. Okay, so see, for example, if you take the previous graph, if third minimum not in the list, then fourth minimum must be required. Okay, then that is one possibility. And third and fourth both can be in the MST. Under assumption third minimum not in this cycle. Third minimum is also out of the cycle. Fourth minimum is also out of the cycle. Third and fourth both are out of the cycle. Okay, then both can be in MST. Okay, third if exist in the MST. Okay, so 1 2 3 not forming cycle, then fourth may not be in MST. Okay, third, assume that this is 1, this is 2 and this is 3, and if this edge is 4, fourth may not be in MST. So if third exists, fourth may not exist. Okay, if third minimum not exist, fourth minimum guaranteed exist, but there is no chance that both can be not in MST. Okay, so both can't be excluded in MST. Okay, so now second minimum we already tested, it is true, it is also true statement. Okay, if third minimum not in MST, then fourth minimum must be in MST. Okay, of distinct edge weights. This works only for the distinct edge weight. Okay, so if not distinct edge weight, we can't say like this. Okay, So max cost edge of every cycle, any cycle the max cost edge not in the MST, whatever the cycle max cost edge is not in the MST. Okay. If cut is there, if cut is there, okay, still if cut is there still, okay, so okay. Right. So I am concluding the session. Okay. So actually some more having planned, but it is time over. So this is all about the, okay, so algorithm marathon program. Just go through it once, these statements is useful for solving the questions. Okay. This is all about the marathon program of the algorithms. Okay. So actually Distress and Bellman Ford and some questions are there, but okay, so time getting out, and okay, you also morning 9 onwards in the live, and live strength is reducing. Okay. So I'm closing the session. This is all about marathon program, and if any further requirement of the examination or post examination, so you can message me, or you can okay, so call me directly, or through the in Made Easy Telegram group also. Every faculty is there, every computer science faculty is there. Okay. So which related to post gate counseling, or okay, before examination, okay, and all. Okay. So all the very best, and you done almost best way, best possible preparation, almost you done. Okay. You are in the almost last one more step. Okay. This 10 more days is very important. So whatever you done whole 6-7 months or 8-9 months or 1 year is one phase, and this 10 days plus that exam day is the one phase. Okay. So ultimately little stress and lot of stress to revise and all. Okay. So but still you have to do your best for completion of the remaining thing and completion of the syllabus. Okay. And give 2-3 more full syllabus tests till 4th or 5th, and after that start revising the things, quick notes or main notes, whatever the way you comfortable. So in a day you may plan like a revising almost 5-6 subjects, something like that. Okay. So short notes is okay. So you can go through PYQ if required, few questions only, not every simple question required to solve here for means this last phase. Okay. So those who are not completed all the subjects also, whatever little you prepared, and just make sure that revise and complete the test series of related to those topics or those subjects. Okay. So means if I am not completed whole syllabus, okay, only done 4 subjects, let me try next year. Okay, you can try next year, that is okay, that is a different thing. With that 4 subjects or 5 subjects, if you done, also do this time now, also do this time. If you get only for 4 subjects, if you able to cross 40 marks, assume that. Okay, next time how much confident you will get, you will feel like I will easily cross the 70 marks. That such a confidence you will get, na. So even how much little you prepared, how much big you prepared, and one topic is left or two topic left or half subject left is no matter. Whatever you done so far, okay, those things make sure that revised as much deep as possible. Okay. So thank you all for your support without break and almost 9 to 2. Okay. So thank you all your support and signing off. Thank you.